Is there evidence for a global flood? When we look at Earth's stratigraphic record, does it support evolution? I'm here with Dr. Howard Feldman, and he's a geologist and paleontologist, and he's going to be sharing his perspective on this and his objections to the global flood and what he sees in the stratigraphic record. So, Dr. Feldman has over 35 years experience in this field, including experience in academia and the petroleum industry. So welcome, Dr. Feldman.
Thank you very much. Thanks for having me. I really appreciate you bringing people on that have alternative viewpoints and alternative data, and that's what we're going to look at today. So I've brought lots of data with me, and you can judge for yourself whether you think where this falls in the spectrum. And so what I'm going to try to do is put the paleontological record in stratigraphic context, and then show, I hope, that the objection or that the test of evolution, such as the discovery of a rabbit in the Precambrian, would falsify evolution if it were ever found. And so I'm going to talk about a lot of different subjects, but try to bring everything together in the end. So just a little bit about me. As you said, I have most of my experience in the petroleum industry. So I've got over 30 years experience working in petroleum, both for government, but mostly for industry. I worked at Exxon for a long time. I've got a couple books out. They're a little bit on the advanced side and kind of expensive. I understand that, but one is on stratigraphy on the left, and on the right you see a book about how to interpret depositional environments in siliciclastics. Siliciclastics are basically shale, sandstone, and conglomerate. So shale used to be mud, and then sand becomes sandstone, and then gravel becomes conglomerate. Those are siliciclastics. And then the deposition of limestones is different. I know those are a little expensive, but there's a QR code. Just for the record, I get no royalties from these. So all the money goes to publication costs and a little bit to SCPM, which is the publisher. So I'm going to go through a few claims that we need to discuss before we can discuss the context of the stratigraphic record. And so the first claim that I'm sure a lot of your audience has heard is that biostratigraphy is circular. And so I know this so well. You know, how do you know the rocks are Cretaceous? Because they have Cretaceous fossils. Well, how do you know the fossils are Cretaceous? Well, they're in Cretaceous rocks. And on the right, I show a few of the typical fossils we use for biostratigraphy. There are many, many more. Coccoliths, these are probably mostly fossils you've never heard of, but coccoliths are marine algae that have calcite shells that occur from about the Cretaceous on. Conodonts are mainly in the Paleozoic. These are tooth-like features from a chordate. And then on the bottom right are graptolites. Let me see if I can turn my laser pointer on. Yep, there we go. And so here's the reality, that the fossils that are used to date the rocks are different than the fossils from the same rocks that are dated by the rocks they're in. So that breaks the circularity. I've looked at a lot of this. I've never seen an example of circular reasoning in biostratigraphy. Now, to get into a little bit more detail, every time unit, so in geology, there's two different ways of describing stratigraphic units in the rock record. One is lithologic variation. So these are formations. So the Morrison formation, the St. Peter sandstone, those are all lithologic. And then there's the time units that we've all heard of, like Cambrian, Ordovician, Silurian, Devonian. And for all those time units, they're defined in a type section, actually a type boundary. And so that is, by definition, where the surface is defined. So, for example, the base of the Devonian, I just threw one example up here. The base of the Devonian, which you see, I just copied and pasted this from the Global Stratotype database. The base of the Devonian is defined as the base of the Monograptus uniformis zone, which is a type of graptolite, which is the base of bed 20. And if you go into the publication, it would show you exactly where bed 20 is in a specific Latin long, in this case in the Czech Republic. And so that's the only place where the Devonian is defined. And then we correlate it away from there using biostratigraphy. So something that confuses me a lot, even among geologists, there's a lot of people that don't understand how this actually works. But if you're going to say you don't believe in biostratigraphy, then you can't use terms like Devonian and Cretaceous, because there's no other way to define them. they're defined exclusively in biostratigraphy. So unless you're at the type section, which is just one location in the world, other than that, you can't use those terms outside of that section unless you accept everything about biostratigraphy. There's no middle ground. Either you do or you don't.
Well, now I think most of us just use those terms because that's the term that will identify a certain rock layer. But even if we don't agree with the, dates and all of that are used.
Well, this has nothing to do with dates. This has
Okay.
nothing to do with dates. Have I mentioned any kind of dates here? I've not mentioned any kind of radiometric dates. In fact, these terms like Cambrian, Ordovician, Silurian, Devonian were all defined in the early 1800s. It has nothing to do with radiometric dates. People back then had no idea what the actual numerical age of those units was when they were defined. So, for example, when James Hall, a famous geologist, mapped the Devonian in New York State, he did it in the 1840s, maybe. And, that was 100 years before anybody heard of radiometric dating or radiometric anything. And it was based entirely on biostratigraphy. So without biostratigraphy, you can't call anything in North America Devonian because there's no way to know it's Devonian unless you use biostratigraphy. There's no other way to do it. So the geologic column doesn't exist without biostratigraphy. I don't know how you would put it together. So if you're going to argue that the geologic column supports any point of view, you can't do that unless you accept biostratigraphy, because without that, there's no such thing. There's just nothing to put your hands around. So let me show you a little bit more about this. This is just one example. And biostratigraphy is still the gold standard for identifying any kind of time unit in sedimentary rocks. It's not radiometric dating, it's biostratigraphy. And so here's an example from the Cretaceous. And so when professional geologists talk about the Cretaceous, they might not even mention the word Cretaceous, because the Cretaceous and all the other zones all the other periods are divided into stages. And that's really what we talk about. And then, so I'm showing an example from the Hutterivian from a recent biostratigraphy publication. And you can see the Hutterivian, which is just one tiny bit of the Cretaceous, is divided into 1, 2, 3, 4, 5, 6, 7 biostratigraphic zones based on ammonites. This is an ammonite. It's an extinct group of cephalopods related to squid. And so the subdivisions that we get from biostratigraphy are very fine in terms of just the numbers of subdivisions per unit. So, we wouldn't even talk about just identifying whether something is Devonian or Pennsylvanian. It's, like, where within the Pennsylvanian are you? On the left, this is the stratigraphic column I'm going to use for everything. So every example I'm going to show you is going to be within this stratigraphic column. I use the radiometric dates as a scale, but they're not really relevant for what we're going to talk about today. And I've abbreviated the names because I can't fit the whole names on there and have it still legible. So it's Cambrian, Ordovician, Silurian, Devonian, and so forth. This black and white column here is actually all the paleomag reversals, and most of them are too small to show up here, but there's been several hundred of them. There's reversals in the Pennsylvanian and earlier too. It's just that the stratigraphic record isn't complete enough that they can actually have an unambiguous record. So that's just going to be kind of our timeline that we'll use for all the examples. So I want to show one example of the use of biostratigraphy, and then we'll move on to other things. So this is an example from the Grand Canyon. So you see the Great Unconformity here, and then the Tepete Sandstone, the Bright Angel Shale, and the Mauve Limestone. Now, kind of an old-fashioned way of viewing these is that there was a time of sandstone deposition, then a time of shale deposition, and then a time of limestone deposition. And people will look at the Tepete Sandstone and say, well, that goes all the way to, however far east it goes, but a long ways, like into the Midwest. And they'll say, well, in modern environments, there's no way you can deposit a sandstone over that broad an area, which is absolutely true, but that's not what happened. If we look at the biostratigraphy, which is on the right, and I'm using this example because it's a really famous example in geology. The O and the G are different trilobite zones. And what you see, the biostratigraphy of the trilobite zone, it cuts through the limestone, then through the shale, and then, the cross-section stops just before it gets into the sandstone. And so what that means, because the order of the fossils is independent of the sedimentology, that means that the fossils aren't responding to any kind of sorting or anything, and they're always in the same order. And so that's the power of biostratigraphy. And so the correct, you could look at this Glossopleura, I think it's Glossopleura is the trilobite zone here, as a timeline. Well, this is over a long distance. That's 200 kilometers. That's a long distance. But what that means is that there was, at any one moment in time, there was limestone offshore, then shale in the middle, and then, which is mud, and then sandstone on the right. So the bottom diagram shows kind of a conceptual diagram of how this would have been deposited. And so the sedimentology of the tapetes includes river deposits. And so we see rivers, and I've shown this very, very simplified, very schematically, but rivers delivering sand to the shoreline. Offshore of the sand, we get mud, and then offshore of the mud, you get carbonate, in this case, limestone. And this is a similar pattern that we see going on today. There's places around the world where you see this similar pattern. And then as sea level rose, it left behind a layer of sandstone, which you can see down here. So all this sandstone down here was deposited at the shoreline when sea level was lower. And so sea level kept rising and leaving behind this layer of sandstone. So there never was a time when there was this huge layer of sandstone deposited. And this is really a central concept in petroleum geology and the way we do petroleum. And it's been proven, this concept has been proven in many different places around the world. And this is called Walter's Law, very famous law, that if you see a succession that doesn't have any unconformities, in this case, sandstone, shale, limestone, that succession represents a lateral distribution of environments at the time that they were formed. So is that clear, or did I go too fast here?
No, it's great. So
okay.
Are you saying that anywhere in the world we go, we're going to see the same ordering of layers, as far as you're going to find trilobites in a certain layer, then you're going to have, whatever index fossil in the next layer, whatever index fossil in the next layer, and it's going to be like that all over the world?
Well, there's different conditions in different parts of the world, so it won't be these same depositional environments. In some parts of the world, you're going to have rivers. In some parts of the world, you're going to have oceans or coral reefs. So it'll be different environments in different areas. This environmental model only applies to these specific rocks. You'd have other environmental models for other rocks. So if you buy my book, which I know is expensive, it goes through all the different siliciclastic depositional environments and all the different conditions. And so everything is local. But this pattern exists for a large part of the Western North America or Western US. I'm not sure if it gets into Canada. It probably does. I just don't know enough about Canada.
Okay, so are you saying then that if we go to a different part of the world, we might have, certain index fossils below, like not in the same order as the index fossils in North America?
Well, I'm sorry, I misunderstood your question. The index fossils are always in the same order. Like you might be missing a zone if there's an unconformity. So there might be gaps in the rock record where you're missing zones, but the zones, if they're not in the same order, that means they're not good zones, and we would abandon that. So this is something that people spend a lot of time. I mean, there's a whole international commission that just looks at this issue to make sure that the biozones are consistent. And they may not be consistent worldwide, but they're going to be consistent over some huge area in order to be useful. And that huge area would likely include different continents, but with the continents in the places they were at that time, not necessarily where they are today. So there'll be faunal zones that cover, but for biostratigraphy to be useful, the biozones have to be correlatable over some huge distance, or else if it's just like I worked in the Black Sea a lot, and the biozones there only work in the Black Sea. So it's very hard to correlate the time outside of the Black Sea to what's happening in the Mediterranean, because they're all endemic to the Black Sea, because the Black Sea is connected to the Mediterranean only by a narrow strait. But for the zones to be useful, they have to be widespread on different continents, which is almost always the case.
Okay, but what did you mean when you said if they're not in the same order, then we abandon it? Because that sounded a little bit strange to me. Do you mean if they weren't in the same order, we'd abandon index fossil altogether?
No. So
Okay.
yeah, this is a very complicated topic, and I'm
Yeah.
trying to cover it very succinctly. What I mean is that there are some fossils that say respond to environmental conditions, and so they're only going to be present when that environment is present, not necessarily because of any stratigraphic succession. And so those just wouldn't be used for biostratigraphy. They'd be used for other things maybe. And so if there's a fossil that only occurs in a certain environment in a certain area, then biostratigraphically, what I meant by abandon, I mean, you just wouldn't use it for biostratigraphy. For biostratigraphy, they have to be widespread. And so just about all the fossils that we use for biostratigraphy, almost all of them are marine. So biostrat is really easy in marine settings, especially offshore marine settings. But in non-marine settings where you get just plant fossils, for example, it's very hard to use biostratigraphy. There is some attempts, but they're so controlled by local conditions, by local environments, and they just don't, and preservation issues. And so it's really marine fossils that occur offshore, like coccoliths. You've probably never heard of coccoliths before, but they're one of the most common organisms on Earth. Any bucket of seawater anywhere in the world, if it's in the photic zone, will be filled with coccoliths. And so that makes them very useful because they're just so widespread. In order to get coccoliths, all you need is salt water and light, and you'll have coccoliths. And so they're so widespread, they're very easy to use. So does that answer your question?
Yeah, so except that I just want to get a little more clarification. So are you saying there are areas that we can't do biostratigraphy on because they don't fit the model?
There are areas where either you can't or it's very difficult. And so I'm going to show some examples later. And what you're looking for in those areas where you don't have, say, any marine fossils is you're looking for, say, a little thin layer of marine that incurs into that area. And then you can sample the marine section and try to get some biostrat from that. So It's not that biostratigraphy doesn't work. It's just that you need, open marine shales are the best place to do biostratigraphy by far.
Okay.
Okay.
Thank you.
Okay. So here's another claim that I want to deal with, and that is that rocks must be interpreted, and we're talking about sedimentary rocks, must be interpreted through a worldview. And, the claim that you've heard, I'm sure many times, we're all looking at the same data, but we have different glasses through which we view that data. And this is not how sedimentology is done. So there's no a priori assumption of depositional age or process or rates. What we do is we collect data, and I'm showing an outcrop here from Utah. So this is I-70. Green River is about 15 miles away. And this is a sandstone, and there's where we took a core. I did this actually my first year at Exxon in 1995. And I'm going to show this example later, but the core, which is right here, there's my core description, and we collected all sorts of data in this core. Well, by we, I mean me. I collected data. And all the sedimentary structures are in symbols here. It doesn't matter what they mean right now. We're going to get into this a little bit later. But every time we collect an observation, whether it's grain size or sedimentary structures, stacking patterns, by stacking patterns I mean, is it fining upward or coarsening upward? All of those observations constrain the conditions during which that sediment was deposited. And so if you have enough observations, you can constrain the conditions based on the physics of the way sand is moved by water. And in this case, we can constrain the conditions to the point where we know this is a river channel. It's not that there's an assumption that it must be a modern environment. It's just that everything else can be eliminated, and you're left with a certain set of conditions that only fit a river. And this gets into uniformitarianism, and this gets a little complicated, but it's important to discuss it. Uniformitarianism is widely misunderstood. The old definition, it's unfortunate that we have two definitions for this that use the same term. That's just unfortunate. But the old definition goes back to Hutton in 1785, and that's the present is the key to the past. And the view that he had back then is that all of Earth's history can be interpreted based on modern processes. So we now know that is not true. I mean, we just know it's not true. There's so many exceptions, too many to mention. And so when we say uniformitarianism today, what we mean is that the fundamental physics of the way things work hasn't changed. So we're making the assumption, for example, that the viscosity of water hasn't changed, the density of water hasn't changed, the density of quartz hasn't changed. But those are the only assumptions we're making to interpret the history of the Earth. That's it. There's no assumption, like there's no worldview that comes into it. It's just based on the physics of the way processes work. So I'm going to go on to the next slide, and this is just one example of how we do this. So this is an example of a whole series of flume experiments that were done in the 1980s. So let me explain what this plot means. So the bottom axis, the X, is grain size. And so when a geologist says medium grain sand, we actually mean something very specific. We actually carry, I meant to have one here so I could show it and I forgot. We actually carry grain size cards with us with a magnifying glass. And we'll look at the sandstone with the grain size card. The grain size will have examples of what medium grain looks like and what coarse grain look like. So we mean those aren't just approximate. Those are very specific indicators of what we mean based on the number of microns. So microns here is 100 microns is 0.1 millimeter. 2,000 microns is 2 millimeters. That's the upper limit of what we mean by sand. So sand also means something very specific. If it's finer than sand, we call it silt. If it's coarser than sand, we call it granules. And then the other axis is the velocity of water, 20 centimeters per second to 200 centimeters per second. And then what they did is each one of these symbols is a different flume experiment with this grain size and that velocity of water. And then we said, well, what sedimentary structures do we get? And so we get, a zone here with ripples, another zone with dunes and upper plain beds and anti-dunes. It doesn't matter, if you don't know what those mean. Very few people do, but I'm showing an example of dunes here. So this is what dunes look like in my sketch. And you have water flowing in the direction of the green arrow, and you have a crest of the dune. They're almost always curved. And then you have some backflow here that actually scoops out an erosional surface in front of it. And here's a dune from a modern tidal flat in France. The top of the dune has been planed off when tide was going down, but you can see this scoop right here is equivalent to this scoop right there. And so when we see these kinds of dunes with a certain grain size, we can then say, oh, well, here's the limit of velocities that the water could be moving for that grain size and those dunes. If the velocity was moving less, you'd get ripples. If it was moving more, you'd get upper plain beds. And so when we use dunes, which make, as the dunes migrate, they make cross beds. I've shown the cross beds here on the side. We can use those cross beds to get very precise information about what the conditions were at the moment those grains were deposited. I think I have an example. Yeah. So this is what it looks like in the rock record. These are cross beds. So these cross beds here are equivalent to this part of the diagram there. And so we have a scale here. So we have the grain size. Well, you can't see the grain size in this image, but we have the grain size and we have the height of the dunes. And using that, we can get very precise information on what direction the water was flowing to within a degree or two if you have the right kinds of exposures. And we can get approximate information on the depth of the water and the velocity of the water. So we'll have a range of depths and a range of velocities. So for this particular example, for dunes, for this kind of cross beds, the range of water depths, typically the average is about 6 times the thickness of the maximum thickness of the dune. So it's about half a meter. So that would be 3 meters water depth. The maximum would be maybe 15 to 20 times that. So 20 times would be 10 meters of water depth. So that'd be the absolute maximum. And then the maximum flow velocity, in this case, I looked this up to make sure I would say this right, is 150 centimeters per second, which is kind of the speed of a medium river. There's nothing particularly dramatic about that. So it's not catastrophic. I mean, the physics of the way these features form isn't catastrophic. And we're going to look at this specific example later on and put it in stratigraphic context. But this is just one example. Of course, when we're describing the rocks, we'd collect lots and lots of observations, each one of which narrows the possible depositional conditions during which it formed. So I think this is the last claim that I want to talk about, that mainstream geologists are ignoring all the evidence for rapid deposition. And on my YouTube feed, I just saw yesterday somebody standing in front of an upright fossil tree saying, those geologists claim that every layer took millions of years to deposit. And, how silly is that? Because you have this upright fossil tree that couldn't possibly have been buried over millions of years. And this gets to me because all of the evidence for rapid deposition, all of it was first discovered and interpreted by mainstream geologists and then later borrowed by creationists. None of it is original to creationism, none of it. And so example, I worked in Kansas for a long time. We're going to look at some Kansas examples. I worked on some deposits that had upright fossil trees in Kansas. And there was a publication from 1963 from this Pennsylvania sandstone that said the trees were buried before they had time to rot. Well, who could disagree with that? No one in the history of geology that I can find has ever claimed it took millions of years to bury a fossil tree, or even hundreds of thousands, or even thousands, as far as I could tell. I mean, maybe there's somebody out there that made some statement like that, but not that I can find. And so,
yeah, and I understand the frustration with that, but I think the point is more, and I can see it. It seems like they're making the claim that geologists are saying that that's what happened, but I think it's more like this. Like, this is what I would like to see resolved: is that why, when you see a tree going through many layers, would you say, okay, that's an example of rapid deposition? But then everywhere else where you would see, layers and layers, you would say that took millions of years.
well, first of all, it's not everywhere else, and everything is the interpretation of depositional rate is based on each individual outcrop. There's no a priori assumption that it must be fast or slow. So there are lots of places where there are, I can't tell you how many upright trees I've seen, and, beautifully articulated fossil fish. And so there is absolutely lots and lots of evidence of rapid deposition. But there's also evidence of very slow deposition. So you have to look at both. For example, this is a photograph of a core. Now, in this photograph of the core, you see an inch ruler there on the left, and I've really increased the contrast. So this is not what it actually looks like, but I've increased the contrast. And what you can see is that this core, there's no bedding left. It's all bioturbated. And this is part of an 80-foot thick section of bioturbated shale. Now, it looks a little lighter than it is because I've increased the contrast so much so you can see the burrows. But all these circular things are burrows. It's all burrowed, 100% burrowed. And so, what I claim is that young Earth creationists are ignoring all this evidence about slow deposition, like bioturbation and like soils, coral reefs, and lots of other indications of slow deposition. And so you have to look at both, not just one side or the other. Look at all the evidence, and the amount of bioturbation, especially in coastal marine shales. And we're going to see some examples of coastal marine shales in the rock record later, is pervasive. I mean, it's just pervasive. There is so much of it. And so when you see this, and the bedding here has been completely destroyed. There's nothing left. If you had a chunk of that, you couldn't tell which way the bedding is. Now, the burrows are squashed because of compaction. These burrows that are ellipses were originally circles. And so that's compaction. That's not the original bedding.
Yeah. How long would you say it takes for an 80-foot section of, sediment?
Well, that's a good question. So modern burrows, we have to use modern organisms because a lot of times the burrows are not unique to a particular organism, so we can't tell what organism did. Sometimes we can, mostly we can't. But in modern systems, if all the conditions are ideal, the burrowing only goes down about a meter, 3 feet. That's it. And so if you had, say, a 10-foot thick sand bed that was suddenly deposited, say in a second, like a storm came through or a tidal wave or something, deposited a 10-foot thick bed, even if it sat on the seafloor for 100 years, it wouldn't get completely bioturbated. There's just no amount of time that would do it because the burrowers just don't go down 10 feet into the sediment. So you have to, and there have been experiments that show it takes a few years for burrowing to get down the full 3 feet and thoroughly churn it to the point where there's no bedding left. So the depositional rate has to be slow enough that you never have more than 3 feet or so deposited at one time, because if there was more than that, you'd be preserving the lower boundary. Now it's obviously gradational. It's not like the burrows go down to 3 feet and stop, they don't go 1 inch further. It's gradational. So to get 80 foot thick, it's got to be dozens of years, maybe hundreds of years, but not a week that you could, because if you deposited 80 foot in a week, the burrows wouldn't never get down to the bottom 70 feet, 75 feet. So you're talking about dozens of years to get that. And this is an extremely common, now this only applies for bioturbation in marine settings. We're going to look at bioturbation in soils, and that's, different animals, different processes. So this doesn't include that. So does that answer your question?
Great.
I'm going into my job right now as a consultant is I teach some of these slides I actually use for teaching petroleum geologists. And so I'm going into like teaching mode. And that's the way I talk to my students.
I love it.
So let's look at, so you asked me to develop some criteria for the recognition of flood. And when I say flood, I mean like a year-long global flood. And so I culled these from a series of videos and books. And so this is the kind of evidence that is used commonly I didn't cite the sources, but I can tell you where I got this from. So these are the criteria. They're not in any particular order for evidence for what is used as evidence for Noah's flood or a 1-year global flood. And so the first is evidence of rapid deposition. We already talked about this: upright fossil trees, complete fossil fish. Now, something about fossil fish that's important is that if you get a complete whale, that doesn't really require rapid deposition, because whale bones are just so big that even if it got scavenged, the bones would be essentially unmoved and they could be buried slowly. And, one time we were talking and you had asked if anybody's ever found whale bones on the seafloor today. And they have. I actually looked it up. I didn't know this. There are complete skeletons of whales laying on the seafloor today. And the meat has been completely removed. I mean, they're just bones. And the thing is that the bones are just so big. Some of them have been disturbed, some of them are partial, but some are almost complete. And so you don't really need rapid burial. The bigger the animal is, the less you need rapid burial to preserve it intact, except if it has like tiny little scales, then you do. So other evidence, I'm just going to go through these. Marine fossils in the middle of continents. Well, there's a lot of times in the past when we had seaways that covered most of the continent. So everybody agrees that when you see widespread marine deposits in the middle of the continent, there was a flood there. The question is whether it was the flood. And you don't really see that today, except for the only one I know of is Hudson's Bay in Canada, which is pretty big. So it's a seaway in the middle of continent. It's got continental crust below it, but it's not covering like half of North America or 2/3 of North America the way some of these things did in the past. Widespread thin marine strata covering much of the continent. This is from Is Genesis History. Dr. John Whitmore said that. Little to no soils or karst. Well, that's just false. I mean, that's used as evidence, but it's not true. And I'm going to show you that it's not true. Very little bioturbation. Again, I've already shown you that that's not true. No river valleys and no river channels. A lot of people have said this. Well, there's no river channels, and that, how can river channels form underneath a flood? They can't. And I'm going to show you that's the main part of what I'm going to show you today. Is there's lots and lots of evidence for river channels and river valleys in the ancient. Little to no erosion and unconformities. Lots of people have made this statement, and it's not true. There's actually lots of evidence for erosion, but in the Grand Canyon, which is one of the most spectacular deposits, spectacular outcrops on Earth, there is actually very little evidence of erosion. There is some, but there's not a lot at some of the bigger unconformities. I haven't really studied that, so I can't address it, but I've looked at, as part of my job, I've looked at hundreds and hundreds of unconformities, and it's rare to find an unconformity that doesn't have a lot of erosion at it. And so I haven't actually studied the Grand Canyon. I was there when I was 12 years old, but I don't think that counts. And then the lack, this is from its Genesis history. They said the lack of a complete ecosystem. And so what he means by a complete ecosystem, he said it's like all the plants and all the animals. So the animals were eating the plants. So you have to have the plants and animals together. And this is from Dr. John Whitmore. They have a whole, they have two videos on this. One is just discussing the evidence for a global flood, and the other is on the Green River Formation. So he claims that in his Genesis history, he claims that the Green River Formation with all spectacular fish fossils has nothing to do with the flood, that was later, and that's a complete ecosystem, and that if you go back to the flood deposits, you don't see complete ecosystems. And I'm going to show that's not true. So I don't know if there's any other criteria that you've come across that I haven't listed here. I've tried to be as complete as I can. Is there anything I've missed, Rebecca?
Oh, well, there might be some things, but I would say when I saw this list, I thought, okay, this is a good list of some of the things that I've encountered. But I will say I'm getting like a little bit like when you say no, there's no this, it actually seems to contradict my own personal observations, not just what I've heard in creationist things, but when you say that there's no that like you're resisting about the layers and the objection that there's no soils in the layers. I mean, I regularly see layers that are supposed to be millions of years old of layers that don't have soil deposition, right? That are just a flat thing, and it's supposed to be the next layer is supposed to be a totally different time period. So I'll be interested to see how you kind of lay out your evidence, but I will say I am registering my objection against you just basically going through this list and saying this isn't true, this isn't true, this isn't true. So I mean, I'll see how it goes.
Well, are you getting an echo? Because I had my headphones on. I realized the sound is actually coming from my computer, which I didn't intend.
I don't have an echo on my end.
Okay, that's good. So
Yeah.
I'm basing this on extensive work that I've done around the world. I mean, this is not based on just a few little observations. And so I'm going to show you, obviously in a YouTube format, I can't go through everything, but I'm going to show you a lot of evidence that shows you how we do that. And so if for example, you're in an area that is completely marine, you're obviously not going to get any soils. You have to be, on the other side of the coast to get soil. So they form only in certain areas, but where they form, it's widespread. And so I'm going to show you specific examples of soils and where we find them, and I'll develop those topics. But I appreciate your skepticism. And, when you go hiking, as I said before, when you go hiking, if you want to take pictures of where you are and record the lat long, so I know where it is and what formation it's in, I can comment on them.
Right. And I don't go hiking that often now.
Oh, I go hiking a lot.
In the various places that I've lived around the world, okay, I see the same types of things in the various places I go. That is, if it's not places that are covered in vegetation. But if it's places that have rock formations, I see a lot of the same things. And one thing that I see, and you can see this in a plane, if you're flying in a plane too, is that everything looks like it has been messed with water. And so it looks like there was a global flood. There's evidence of water, large sedimentation that could only be deposited by water. And even in your description, you're talking about all this, things related to water. So for me, there's tons of evidence of a global flood. And so, I just don't see how it's not, how you would say that it's not evidence of a global flood.
Well, I'm going to develop that.
Okay.
That's what I'm going to talk about. So we're going to go through specific examples. And first I'll say although the vast majority of deposits are by water, not all of them. There's the Aeolian sands in Utah, the Wingate, Entrada, and Navajo sandstones have sedimentary structures that are unique to wind. They cannot form in water. So there's a lot of evidence of widespread subaerial deposition. But having said that, the vast majority of strata everywhere in the world are deposited by water, but not all. So we're going to get into some specific examples. Here's a map of North America during the Devonian. I'm going to get into that in just a second, but I'm going to highlight 3 areas in Kansas, Utah, and Alberta. The reason I'm picking these 3 areas is because I've worked this area extensively. I'm going to rely as much as I can on my own work, supplemented with a few other examples. And so I've got some stars here of specific outcrops and subsurface data sets we're going to look at. And then this red line is a cross section that goes from the Grand Canyon up to just north of Zion. So I'm going to get back to biostratigraphy. One of the criticisms I've heard is that there's no place where we see the complete geologic column, that is, from Cambrian up to the top of the Cenozoic. And it's probably true that there's no place where we see everything, but there are lots of places where we see almost everything. So if you look at this cross section, so this is a geologic cross section of what it would look like if you actually dug a trench, all the way down to the Precambrian along that red line. And so in the Grand Canyon, you have the Precambrian and the Cambrian. You're missing the Ordovician and Silurian, but then you have the Devonian, Mississippian, Pennsylvanian, and Permian. And then as you follow the surface along, you come to the Triassic, and then the Jurassic, Cretaceous, and then the Paleogene. So that's, 90% of the geologic column in this one area. So I don't understand this concept or this comment I've heard a lot that there's no place where you see the geologic column. Well, there are lots of places where you see it. And so if you were to drill a hole, from here all the way down, you'd go through almost everything, missing the Silurian and the Ordovician. So there's no place where you see the whole thing, but there is a lot of places where you see almost all of it. Another criticism I've heard is, well, if somebody found a Precambrian rabbit, they just would say it's not Precambrian anymore, it's something else. But that's not possible either. If you look at the Precambrian sediments that are shown in the Grand Canyon, if a rabbit was found there, and when I say rabbit, I mean like any modern animal. I mean any modern terrestrial animal. There's never been a terrestrial animal anywhere found in the Precambrian. Not a footprint, not a bone, not a tooth, nothing. If there was a Precambrian rabbit that was found, you couldn't just call it a younger bed because it's overlain by the Cambrian. So you can't physically make it younger than what's on top of it, right? I guess you could say, well, maybe, geologists would say there's a fault there, but, you can't just make up a fault without having any evidence of it. And that wouldn't be sufficient. So this idea that if you found a younger animal out of place, you would just rename the age of that unit is not possible because you're constrained by the units above it and the units below it. So you can't physically make it younger. Now, there might be a few places around the world where those constraints don't exist, but that would be exceedingly rare. So, that can't be done. So, the objections I've heard to biostratigraphy and why it doesn't work, none of them that I've seen hold up. And I'm trying to walk through, specific examples of why they don't work. So,
okay, before you start, can I ask a question about this? Because I was like, my understanding is that like North America as we know it has only been in its current form for like 200 million years. So right now we're talking about before that, right? So where was this located?
I don't have a world paleogeographic map handy.
Okay.
But if you go onto YouTube and type plate tectonics, you'll find probably 100 or 200 videos that show the evolution of the plate tectonic history over time, and you can usually they label the ages, so you can just stop the video at Devonian and see where the world was. North America was isolated from the other continents, and I guess I had space here. I could have put in a world map there, and I just didn't do it. I should have.
No, that's okay. You can't predict every question. But this is, I just want to be clear what we're talking about. So this would not have been North America as we know it, because this is prior to.
Well, the main difference is the West Coast doesn't exist yet. So notice where the map stops. There's Idaho, right? So California, there's no land out there in California. And so that land was accreted later on. But, the middle of the continent hasn't really been distorted very much. So there's, some parts are different and some parts are not very different. So what this map is showing, it's a paleogeographic map, but one way to look at this is that every place you see blue on here, whether it's dark blue or light blue, there's marine Devonian layers. So in Alberta, a lot of this Devonian is limestone. When you get into the Appalachian Basin, which is over here, that's the Devonian Marcellus shale. And so that's one of the oil shale. I bring this back to petroleum. And so wherever, this is obviously highly artistic, but wherever you see land, that's where the Devonian is missing. So like there's thick Devonian, I think it's almost a kilometer, but there's huge thick Devonian in the Hudson's Bay area, but not in between Hudson's Bay and Saskatchewan. So these are where there's land. So here's the first question I'll throw out to the audience is, in Utah and in Dinosaur Provincial Park and other places in Alberta, there are lots and lots of dinosaur bones and dinosaur footprints. So if you're thinking that this is part of a 1-year flood, where were the dinosaurs at this moment in time? Like, do you think that if the dinosaurs were here, did they run a couple thousand? Well, I guess about 1,500 kilometers to leave their footprints in Dinosaur Provincial Park. I mean, how did they get there? And one of the concepts I've heard many times is the order of the fossils, and we're going to get to that later on. But the order of the fossils is the order in which animals were running away from the flood. That is, like mammals could run the fastest and amphibians or frogs the slowest. But to get the footprints where we see them today, the animals had to be running the other way. They had to be running from the land towards the ocean at that time if dinosaurs existed. Now, in mainstream geology, secular geology, dinosaurs didn't exist yet. This is the Devonian. There are no dinosaurs or mammals for that matter. And so you had, a couple 100 million years from when this layer was deposited to when you get the footprints here or the dinosaur footprints here. And we're going to look at footprints here as well in the Pennsylvania, not dinosaurs, but other animals. And so, every place in North America that I know of where you have dinosaur footprints, beneath it are open marine layers that extend for hundreds of miles. And so if you're doing this in a 12-month period, I don't see how the animals got there to leave their footprints. I mean, they had to be living there in order for the footprints to be there. So
yeah.
Go ahead.
Well, I'm kind of confused about this because, like, since I do live in Utah and I've seen a lot of dinosaur footprints, I'm wondering why are they all on the surface? Like, if these are like 100 a million years ago, then like why do we have so many on the surface? Why do we have all these 100 million-year-old exposed rocks? Like, I thought we were building sediments over time. Why are we like, so I'm confused about this point that you're making, because to me, when I'm thinking about, where I can't see the problem here.
So if you look at this cross section again, the only places you find dinosaur footprints is where the Earth's surface intersects the Cretaceous or Jurassic, and maybe uppermost Triassic. There might be a few. So, for example, in the Pennsylvanian and Permian, there are no dinosaur footprints. So it just depends on how much erosion has proceeded to get down to whatever layer you're at. So if the Earth's surface is at the Cretaceous and it's a non-marine Cretaceous deposit, yeah, you'll find dinosaur footprints. I've seen lots and lots of them out in the field. But again, only where the Earth's surface intersects the Cretaceous or the Jurassic. So it's not like, how did it happen? It's just that you're there in that particular place where the erosion has gone down to that level. So, but below the dinosaur footprints are widespread marine units. And so then how did the dinosaurs get there in a 12-month period of time? I don't see how that's possible, frankly. And the idea that they're running away from the flood, if you look at the actual succession of strata, in order for the dinosaurs to get there, they had to be running downhill towards the flood. They had to be running from the land area downhill as, I guess, floodwaters receded and then came up again, and then receded and then came up again. And so I think there is a very large problem of how, like in Dinosaur Provincial Park, right where I have my arrow, you walk on the ground there and it's just littered with dinosaur fossils. I mean, just your feet are just about crunching the bones as you walk across them. And you can look online. I'm not going to show an example, but you can look online and find dinosaur footprints in that area, and lots of river channels and things. And I'm going to go into that evidence later. But you had to get the dinosaurs to there, and if they're living now at this moment in time in this map, they had to be living on the land. And so it's how did that happen? And so it's not the question of why did the land just erode down to that one level. It's eroded down to every level. It just depends on where you are, what level you're looking at. Does that make sense?
Still not really, but I don't want to hold us up at this point too much. But
Okay.
I do want to get clear on what is below those dinosaur footprints, because you said there's marine layers.
Yep.
But what are we talking about? So,
Well,
like Utah, for example, I know you've done a lot of work here. So, if those places where I can see dinosaur footprints right now, what are you saying is below that?
marine rocks. If you
What
go
do you
deep
mean
enough.
by marine rocks?
Marine limestone, marine shale, layers that go for hundreds of miles that are filled with marine fossils. So like the Devonian. So the Devonian is, there are a few places where the Devonian has been eroded away, like in the San Rafael Swell and some other areas. But, wherever you see Cretaceous rocks, like dinosaur footprints, if you drilled straight down, you would encounter Devonian marine rocks below it, which is the basis of this map. And there's, thousands and thousands of petroleum wells that have done this, and there's stratigraphic tests. So there's enough subsurface data to show that this is what's going on.
Okay.
So you had to get, the widespread marine deposits, especially in the Paleozoic, precede all the footprint layers that I know about.
Okay, that's really interesting. And this is something I haven't heard before. So I'm very interested to follow up with that.
We're going to look at some specific examples.
Okay, cool.
So here, we're going to go to Kansas first. This is an area, I worked at the Kansas Survey for 7 years. So I know Kansas geology very well. So we're looking at first we're looking at a geologic map of Kansas. So all the yellow and orange, this is all recent stuff. So we're not really paying attention to that. That's just kind of the least, just a little bit on the top. So you've got Cretaceous in green, And this is the worldwide standard green color for Cretaceous. You may not have realized there was a worldwide standard of color for the Cretaceous, but there is. And then the Permian, and then the Pennsylvanian, and then down the corner here is the Mississippian. We're going to talk specifically about this location called Garnett in the middle of nowhere in Kansas. And then the cross-section AA prime is going almost exactly along I-70. And so here's that cross-section. This is from the Kansas Geological Survey website. So here's thickness here. So that's 2 kilometers. This is sea level right there, the 0. And then, as you go from west to east in Kansas, you're going downhill. So you're encountering the Cretaceous here. And then as you continue going downhill, you encounter the Permian. Continue going downhill, you encounter the Pennsylvanian. And if you're continuing to the right into Missouri, you would encounter the Mississippian and the Ordovician as you continue to go to the east and to the southeast. So, when you say why is the land surface at this particular area, it's this particular layer, it's at every layer, just depending on where you are due to modern erosion. And or due to ancient erosion. There's actually an unconformity at the base of the Cretaceous here. This is one of the big mega sequence boundaries that some people like to talk about. So there's a huge, not a huge amount of time. Well, in this case, there is a lot of time missing because you're missing all the Jurassic. This is the Morrison formation that just barely gets into Kansas in the subsurface, but it doesn't outcrop. So is this clear? So what I've done is I've taken Garnett, the location we're going to look at, and just projected it onto this cross section, so it's approximately here. Okay, and we're in late Pennsylvania. So in Europe, they use the term Carboniferous, and in the U.S. and North America, we use the terms Mississippian and Pennsylvanian, but they mean the same thing. And so we're in late Pennsylvanian time here. Okay, so we're going to look at Garnett. So this is a project I did many, many years ago. So this is a stratigraphic column just showing the Pennsylvanian for just a tiny, tiny bit of the Pennsylvanian here. And the theme I want to go over is what's called cyclothems. This is a particular type of stratigraphy. Don't worry about, these are the names of all the stratigraphic units, so just don't worry about that. So everything in blue in this stratigraphic section is limestone, so both dark blue and light blue. These straight lines represent marine black shales. These are organic rich shales. And so you have marine limestone and some marine shale, then a valley, then more marine limestone, another valley, marine limestone and marine shale, another valley. And then this goes on for 8 cycles. These marine strata, so this one, I looked it up. This extends from Oklahoma to western Pennsylvania. This marine black shale extends from Oklahoma to eastern Pennsylvania. So that's like 2,000 kilometers. So there's each of these cycles, you're completely submerging the Midwest under marine layers. And then the sea goes down, and I'm going to show you proof of that. And you form soils and valleys, and then sea level comes up, and you form these widespread marine deposits that blanket the middle of the continent, and then sea level goes down, and you form soils and valleys again. And I'm only showing you 8 cycles here, but in the Pennsylvanian, it's hard to count the number of exact cycles, but it's about 50 or so of these cycles in the Pennsylvanian. And so we're going to look at this Garnett Valley first, and then we're going to look at the Tonganoxie. So these are 2. I studied all of these, but these are the 2 we're going to look at because we have a lot of data. So here's my publications at the bottom here. This is a publication I did amazingly 20 years ago. And so this diagram comes from that publication. And then this is a broader publication by Phil Heckel, where he shows data for 36 of those 50 cycles. And so he goes into more detail, and it goes into the biostratigraphy of this. So here's one of those valley. When I call it a valley, that's clearly an interpretation, and I'll show you why we're making that interpretation. So these are these limestones that go for hundreds. Some of them go for 1,000 kilometers. So we've got marine. This is all marine limestone here, and then you've got an incision. and then you've got more marine limestone on the top. So this limestone right here in dark blue is this limestone right there in the photograph. And then this surface dipping down here where the stoner limestone has been eroded away is that surface right there where my staff is resting. And then this is just a pile of debris behind it. That's not rock. So this area was excavated. This was all covered with shale, and it was all excavated for terrestrial fossils, for fossil vertebrates. So, and I'll show you some evidence of that in a minute. So that's why we can see this sloping surface. This surface was just a couple of years before I took this photograph. This surface was completely covered with rock, and the rock has been removed so they could get at the terrestrial fossils. Beautiful terrestrial vertebrates here. So the bottom of the incision has limestone conglomerate. So this is the core. So we took 4 cores. These are the 4 cores, and I'm using those to draw a cross-section of the valley. I should have said that. This is a valley cross-section. And so the bottom of the core is this conglomerate. And so all these clasts, like all these circles you can see, those are all chunks of limestone that were eroded. It's exactly the same kind of limestone that you find in the marine limestones on the sides. And again, those marine limestones go for hundreds of kilometers or hundreds of miles even. And so the interpretation is everything was submerged, like almost the entire state of Kansas was submerged and beyond, into the Midwest. And then sea level went down to erode this valley. And I'll show you evidence of that in a second. So there's marine fossils in here, but you can see they're truncated at the edge of the clast. So these are marine fossils, like that's a shell of some sort, and it's truncated at the clast. And so that was eroded from one of these 2 limestones. I don't know which one. So we're going to look at some of the sedimentary evidence from this. So here's, this is an outline, a silhouette of a pelycosaur. I mean, that's one of the animals that they're going after here. And so it's in the terrestrial fossils are all from this upper shaly section here. And so here's a couple of footprint trackways. Here's a couple of other footprints. So pelycosaurs have a very distinct footprint. It looks like a hand, like a human hand, but he's got 5 digits, 1, 2, 3, 4, 5. And what's the thumb is actually the pinky. So this looks like a right human handprint, but it's actually a left part of the trackway. So the right part of the trackway would be over to the right. So it looks like a human hand, but it's not. So these are the fossils that have been published from here. So it's got insects and scorpions, sauropsid, that's a type of reptile, another type of reptile, pelycosaurs. There are some primitive amphibians, temnospondyls. There's no, in the Permian or Pennsylvanian or Paleozoic, there's no modern amphibians like frogs or salamanders. Those don't exist. There's a few marine invertebrates. I think from the field work I did, I think they're all out of place or just eroded from the valley walls. But what's really important to me, I think important evidence, is that in all the Pennsylvanian around the world, there are lots, like hundreds or thousands of terrestrial fossils. No one's ever found a mammal. No one's ever found a dinosaur. And no one has ever found an angiosperm. So angiosperms are flowering plants. They're called flowering plants, even though a lot of times a flower isn't obvious. But it's basically almost every plant that we eat. So all the grains, fruit trees, oak trees. So the plants that wouldn't be included are things like conifers are not angiosperms. Ferns are not angiosperms. But just about everything we eat is an angiosperm. And there's not, and even angiosperm pollen. No one has ever found any angiosperm pollen in the Pennsylvania. And they've looked. I mean,
okay. Now this is where the like, how do they figure out what is the Pennsylvanian? And this is where, like, I'm feeling the circularity, because how do you decide that it's the Pennsylvanian? Because earlier you were telling me it's mostly done on biostratigraphy, and now you're telling me we never find certain things in the Pennsylvanian. But because I'm wondering, did you label it Pennsylvanian because you found certain things in it and you didn't find other things?
No. So the answer to that is the age comes from the marine strata, and it comes from conodonts and forams. That's what determines the age, not this. So that breaks the circularity. So the age is not determined by the presence of mammals or the absence of mammals. That does not determine the age. It comes from, and in this section, it's a lot of it is conodonts, which come from these thin black shales like that one right there and others. And there's also a particular type of foram called a fusilinid, which is used for biostratigraphy. Forams, let me back up. Everybody knows what an amoeba is, right? A foram is an amoeba type organism that has a calcite shell, and they're very specific types of. Some of them, they just look up foram in Google, and you'll find lots of photos. And so it's the marine fossils, especially fusilinids and conodonts, that are used to determine the age. Not this. This is the age of these is determined by the age of the marine rock. So there's no circularity.
Okay, but how do you know the age of those creatures?
This goes back to the type section. So somewhere in the world, I don't know where, there's the type section for the Pennsylvanian, and that's where the Pennsylvania is defined. That's by definition the Pennsylvanian, and I assume it's in Pennsylvania someplace, but I haven't actually looked it up. Mm-hmm. And then at that one location, we say that is by definition the Pennsylvanian, and then you sample the biostratigraphy in that one location, and then you correlate it laterally. And so there's no circularity in any way.
I don't know. I'm still feeling the circularity.
Well, you can.
I'm not sure what you're like. I'm not sure how you're determining the age on this. Like you're
from the forams and conodonts. That's where the age comes from. Not from the lack of mammals. If somebody found a mammal in here, well, let's go back to the cross section. If somebody found a mammal in this location, you could not say that it was younger because it has the Permian on top of it, and on top of that is the Cretaceous or the Jurassic, and then the Cretaceous. So the age of this is locked in. You can't change it. And that's not that there's some a priori assumption that must be the age. It's through, we're seeing the result of 100 years of work, working out the biostratigraphy of these units. And the biostratigraphy in this area, I know because, I've read the papers. I haven't actually done the biostratigraphy myself, but certainly a lot of people have. And the biostratigraphy is determined by the marine strata, not by what's in the valley fills.
Okay? Right, but how do you determine the marine strata? How do you determine, that layer is a certain age? And you said this was done way before radioisotope dating. So how did they figure that out?
By reference to the type sections. So every age, Pennsylvanian, Permian, Cretaceous, the type section for the Cretaceous is outside of Paris. I don't know where the type section for the Permian or Pennsylvanian is. I haven't looked it up, but there's a type section someplace. Plus, when you sample a thick stratigraphic column, the order of the marine organisms is consistent around the world. There's always some local fossils that occur in this area, not that area, but the overall, many of the marine fossils are the same, and they're in the same order. And so then the type sections are chosen very carefully to not overlap, and it's correlating from the type area to here. And as you said, and you're repeating what I said, is that all of this was worked out before radiometric date. So there's nothing to do with radiometric ages, nothing. And the way the radiometric ages are worked out is that if you find, say, the boundary, some biostratigraphic boundary, and you want to know what that is in years, the way that's done is with radiometric dating by finding, say, a volcanic ash bed above it and a volcanic ash bed below it, and then that constrains the radiometric age of this. But we're not talking about that. I mean, since you asked about it, I'm saying how it's done. But all of this was worked out, I don't know when the Pennsylvania in Kansas was mapped, but I'm sure it was way before radiometric dating. I know New York State, because that's where I grew up. And the Devonian of New York State was mapped in the 1830s or 40s or 50s, something like that. And I'm sure this was mapped in the 1800s.
Yeah, and I don't want to drive you crazy, but I just have to point this out because I want to share with you where my doubts are about what you're saying.
Sure, that's why we're here.
And so, like, my concern, and I've seen this a lot, is that when data doesn't fit, it gets thrown out. And so I even feel like I heard you do that in this conversation, because you were like, oh, we find a few of these certain marine fossils here, but I think those just came in, like, basically, like you kind of like made a reason for why,
No, I didn't make it up. It was based on observations from the field work I did. I'm not making it up. I mean, if there were marine fossils there, it wouldn't be a problem. I'm just saying I don't think they're endemic to that location, because they're the types of fossils that are found in the limestone. They look to me like they've been eroded from the limestone. So it was just, I wasn't trying to dismiss something because I don't like it. There's no reason why I wouldn't particularly like it, but that was my observation based on field work.
Okay.
Not based on, yeah, but so there's absolutely no circularity in the ages, none, because the ages, these are the fossils that we find here, and the age is from the marine strata that are being truncated. So we know the age of this incision has to be older than these units that are truncated and younger than the unit that goes on top. And lateral to this in the Rock Lake Shale is very thin here, but lateral to this, where the Rock Lake Shale gets a little bit thicker, there's a beautiful soil, particular type of soil called a vertisol, that only forms in well-drained settings. So sea level had to go down, and to get the footprint, sea level had to go down. So the sea level depth to get these marine limestones, as I said, these marine limestones extend for hundreds of miles in every direction. So sea level had to be deep. So some people have thought that these black shales, well, you don't see a good one here. Yeah, this black shale. That's a black shale right there, the Eudora. Some people have claimed those black shales were deposited under thousands of feet of marine water. I don't know if it was that deep, but you had to submerge like all of the Midwest to get that. And so at least hundreds of feet deep, if not thousands. But to get the footprints here, you had to be above sea level, because these are animals walking around. These are terrestrial animals. And even more convincing here are raindrop imprints. I like raindrop imprints because they're easy to show and they look kind of cool and they're easy to understand. So to get raindrop imprints, and there are a lot of raindrop imprints here, sea level had to be below the level of the sediment. And so this is a terrestrial deposit. I mean, you can't, the sea level had to be below the level at which these deposits were formed. And yet, immediately before it, sea level was very high, and immediately after it, sea level was very high. And there are 50, give or take, of these cycles in the Pennsylvania. And so I showed a plant fossil. There are no angiosperms in these deposits. As I said, no mammals, no dinosaurs, no angiosperms. But we do get a lot of conifers, beautiful, beautiful conifers, and fossil charcoal. I'm using a technical word. This black stuff, I know you can't see the details, but everything that's black here is charcoal. So it suggests that there were forest fires in the area, and the charcoal got preserved in these deposits. There's my knife for scale, a knife that I lost many years ago. All right, so this is the last of this. I'm going to go on to another valley system. Okay, so what's really important here is that there's soils in the Rock Lake, the Rock Shale, the Rock Creek Shale member, although not here, and the details are in our publication from 2005. And the sedimentary evidence from this incision is that all of this was deposited above sea level. But all of this, everything in blue, was deposited below sea level. So sea level was high, then it went down, then it went up again. So let's look at one other example. We're going to switch to the Tonganoxie. And so here's a map. This wasn't by me. This was previous work of the Tonganoxie. This forms a valley. So you see a valley with two tributaries here. And then as you go up here, there's two more tributaries. I just did a quick calculation of how much sand, and I got 18 cubic kilometers of sand. So what would that be? Something like 10 cubic kilometers of cubic miles of sand. So it's a huge volume of sand, and we're going to look at the sedimentology of that. So we did a study right here. So there's Feldman et al. 1995 and Lanier et al. 1993. We did a study in this area right here. And so this is when I was at the Kansas Survey. So here's our map of that valley. So this is the thickness of the valley fill. So here's a schematic cross-section of the valley. So we're looking at the thickness from this limestone down to here. So here's marine limestones that go for hundreds of kilometers or miles. And then here's the valley incision in red. And so here's a map of it. So there's Lawrence, Kansas. So I-70 would go like right here. There's the Kansas-Missouri border. And so the darker the color, the deeper the incision. So it gets up to about 40 meters deep. And so what you see here is a main valley going down like this. And we know from the paleocurrents that the water was flowing to the southwest. And then these are all the tributary valleys. And now we can't map the tributaries any further than this to the southeast because it's been eroded away. So you lose the outcrop. So this is, I started by showing you a very small valley. Now I'm showing you a much bigger one. And so this valley and the sand in the lower. So I'm going to show you an example of this kind of sand and an example of that kind of sand. And I'm going to show you some coal. So the sedimentology of this sand is consistent with rivers. And I'm going to show you that when you look at the sedimentology of the sand, the water cannot be up here. It has to be lower than the valley is high, because otherwise it's not consistent with the sedimentology. Okay, and I did this map was made with hundreds and hundreds of subsurface data sets. So here's what the sand at the bottom, we looked at this photograph before. So these are trough crossbeds from 2D dunes, and the sedimentology, our paper from 1995 goes into details. We actually brought in an expert on river deposits to look at this, and he decided this was probably from a particular type of river called a braided river. But you can work out the direction the water is flowing, the depth of the water very approximately, and the speed of the water. And so the depth of the water can't be more than the depth of the valley, so that there's no way that the water was deeper than the valley is deep, that it had to be less. So that meant that the edges of the valley on the sides had to be subaerially exposed. It had to be, just the physics of it. I'm showing an upright tree. I actually collected this and then photographed it in the lab, and you can see how big it is. Here's a very small channel. There's my rock hammer for scale. And the currents are actually going back and forth. So we actually interpreted this whole deposit here as a tidal flat, a muddy tidal flat with the currents going in and out. And there's one spectacular spider fossil that was found here, not by me. This is a museum specimen, but lots and lots of plant fossils in here. I used to take dates to this locality. We'd crack the rock open and collect fern fossils and things. This is another part of that same valley. Here's a coal. This is marine shale. And again, these marine deposits go for hundreds of miles. There's a tiny little soil here, and then coal, and then this deposit right here. And we interpreted this as a tidal flat. So here's more footprints. So again, like, how did the terrestrial animals get here? Because there's marine deposits immediately below it. There's marine deposits on top. The marine deposits below it go for hundreds of miles. So where did these terrestrial animals come from to get here? If you have 50 cycles and you think all of this happened in less than a year, the animals would have to run, hundreds and hundreds of kilometers or hundreds of miles to get here, where the area was previously submerged. We're going to look at a map in a second. Raindrop imprints, more raindrop imprints. I like these because, they indicate that you have to be above sea level. And then these are really cool. These are different colors because they were photographed in different lighting. This is rock from this outcrop, and these are actually foam bubbles. So you can imagine as the tide is going down, and there's little clumps of foam, like the way soap bubbles clump in your sink when you're doing the dishes. And as the tide goes down, we think this is intertidal. It just gently lets these little bubbles of foam on the surface, and they form a little imprint. Now, we've used very low angle lighting to make it look like they're craters, but these are very, very tiny. And then I just put this in here because it's so cool. These are fish fin drag marks. So the idea is, as the tide is going down, the fish are getting squeezed between the water level and the sediment, and as they're swimming away, they're leaving imprints of their fins as they drag across the bottom. So this is all intertidal, and so that means we're right at the shoreline. This would be a tidal flat. And our paper from 95 or 93, Lanier et al. 93, goes into all the details of why we think that's intertidal. So here's a map that shows what it looked like in the Pennsylvanian. And so this line between the blue and the brown is where the shoreline was, or where the transition is between marine and non-marine deposits at the highest sea level, like those marine limestones and black shales that go forever and ever. And then the red line is the low stand shoreline when sea level went down. And so not every cycle was this dramatic, but some of them were. And so here's the little valley that we were just looking at. So, there's 50 of these cycles, give or take, in the Pennsylvanian. And then here I actually did include not quite a global, but a paleogeographic map. So when we did this, we put the equator here. I noticed in the newer map, so this seaway right here is this seaway right here. They're putting, I showed all these different land masses, and they've lumped it all together in one here. But they have the reason I put this in there, they have the equator a little bit further north. But we know the equator was in this orientation because of paleomag. So paleomagnetic measurements tell us what direction magnetic north was. And so you have to rotate the continent to get that to work. And so these days they can do paleomagnetic work on shales, which is amazing. It's not just igneous rocks. And so we know the orientation of the equator, but there's obviously a little, my map has it down here, and this map has it a little bit further north by the ancient standards. So then, when you look at all the evidence from all the soils that are here, the paleosols and the river valleys and the footprints and the raindrop imprints and the, open marine strata that just go for hundreds, if not couple thousand kilometers. You have to have marine cycles of high stand and low stand, where sea level goes up and sea level comes down. And you have to somehow get the terrestrial animals into these locations. And if you use radiometric dates, and I don't want to get into that discussion because it's not something I'm prepared for, but if you use radiometric dates, the standard interpretation is that each of these cycles lasted about 400,000 years. If you have a creationist view, you'd have a couple days maybe for each of these cycles. I don't know how you would physically fit it in. Now, there are some young Earth creationists that think that the boundary between the flood and pre-flood is late Paleozoic, so this would be pre-flood. This would be Ken Coulson has a channel on YouTube, Creation Unfolding. That's the name of it, Creation Unfolding. And so he's got a whole series of videos. He's a PhD geologist who specialized in stromatolites, which occur in the Precambrian, and he uses that as evidence. And he claims that it's somewhere in the late Paleozoic where the boundary is between the flood and pre-flood. The problem with calling, a lot of people will cite these marine limestones that go forever as flood deposits. Well, they are a flood deposit, but it's one of many floods, and so you need time for the rivers to form and the valleys to be eroded, the rivers to be deposited, and all these terrestrial fossils to be preserved along with the raindrop imprints. And so I don't see how that happens. And, when I listen to a lot of creationists talk about the lack of river channels and the lack of river valleys in the rock record, you now see why I don't think I know it's not correct. I mean, there's lots and lots of evidence for this. And I'm going to show you even more when we get to the Cretaceous. Any questions before?
I do want to ask. So, what would be Ken Coulson's explanation for the marine fossil layers being below the terrestrial footprints, like the dinosaur footprints and such?
Well, he thinks this. That's a good question, and I don't know. I haven't. I've interacted with him a little bit. We've emailed a little bit. He was actually going to buy my book, but if you think it's expensive in the U.S., he's in Australia, and the shipping costs to Australia are insane, and so he didn't buy it, and that's kind of where our conversation ended. And we're looking for a printer other places in the world. Shipping costs in the U.S. are like $6. Shipping costs to Australia are like $100. I mean, it's just insane. It doubles the price of the book. So, and that's kind of where we left our conversation. But he uses stromatolites as evidence of how fast these deposits formed. And so that's why he thinks that it's, he doesn't know exactly where the boundary is, but he thinks it's possibly late Paleozoic. So, but I didn't, we didn't go beyond that.
Okay, interesting.
So then the question is, in a conventional framework, what's the evidence for, like, what's the mechanism for sea level going up and down? And it's glaciations. So, and this goes back to Alfred Wegener in 1912. He used the evidence for glaciers around the South Pole as part of his evidence for how he was going to reconstruct Gondwana when he presented continental drift. So here's part of that evidence. I'm going to go into this a little bit. So this is an interpreted climate cycle for the Phanerozoic, and every place you see blue is where there's glaciations. So obviously there's glaciations very recently. And so one of the evidences for multiple glaciations is what's called Delo-18. So there's two kinds of oxygen in water, oxygen 18, oxygen 16. Oxygen 16 is 2 fewer neutrons, which seems like an immensely small amount of mass, but it actually makes a difference in how water evaporates. So when water evaporates, more of the 16 water evaporates than the 18, because the 18 oxygen is heavier. And this is measurable. This is something that can be measured. And so when the glaciers build up, they build up from fresh water that has evaporated and then rained down as snow. And so that is depleting the oceans in oxygen 16. And so what we see is today, this is where we are today, and this is going back in time. And so I'm using radiometric dates, but you can ignore that. If you wanted to use biostratigraphy, that would work. Or there's I didn't get down a little bit deeper here, but there's a paleomag reversal right there that you could use. And so during glacial times, the seawater is depleted in oxygen 16. And so you have a glacial time here, 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 here. And I wanted to show what some actual data looks like. So this is a core from Portugal, offshore Portugal. And so there's 30 meters of core, and here's the, all the, several hundred measurements of Delo-18. And so you can see this is modern times here, then depleted in oxygen 16, then enriched in oxygen 16, and then depleted. And so we have these multiple cycles of glaciation, and the idea is that in the Pennsylvanian, that's conceptually what could have been going on. And that gives you these cycles of sea level going up and down. So every time the glaciers melted, sea level went up. And every time the glaciers formed, sea level went down, because you're moving water from the ocean to the glaciers. And so with the last glacial cycle, like right here, sea level was down 120 meters below where it is today. And we see that evidence all over the world, like on the coastal shelf, where the shelf goes out into the ocean. If you core down just a few meters below the surface, you get into river deposits, and say the Gulf Coast, where I've worked a lot. And so here's a map. Here's a book that you can get that goes into all the details of why we think there's evidence for glaciers. But all these gray areas have evidence for glacial deposits. And so India, you have to bring India back to where it was for that to make sense. Now, in the middle of Antarctica, you don't get the evidence because everything's covered with modern glaciers with ice. So we don't know what the geology is down there. But in South Africa, South America, Australia, India, and a little bit in Antarctica, There's glacial tills and other evidence. This book goes into lots and lots of evidence for glaciers, and they see evidence for cycles. And we know the ages of the glacial excuse me. We know the ages of the glacial deposits because there's marine deposits above and below them, and we can date the biostratigraphy of the marine deposits. So that's how we know that this is late Paleozoic glaciation. So this is kind of independent evidence, but the evidence for this glaciation has been known for 100 years or more. I don't know when it was first discovered. All right, so we're done with the Pennsylvanian. We're going to move into the Morrison near where you live. So here's Salt Lake City, and then here's the Morrison. So let me just explain kind of what we're looking at here. We're up in the Jurassic, up here. The Morrison Formation is very famous because of the many, many dinosaur fossils that have been found there. This is showing the extent. So the Morrison Formation, the type section, so time units like Jurassic have type sections, but also formations have type sections. So the formation, the Morrison Formation, the type section is actually in Morrison, Colorado, not too far from where I live. And the Morrison, because it's so thick, it's been divided into members. And so this is what you find right around Green River. This is the section around Green River, Utah. So there's 3 members. The Tidwell is a freshwater lake member. It's limestones. We're not really going to talk about that. And then the Saltwash member is about 300 feet thick, and we're going to talk about that a lot. And then top of it is the Brushy Basin member, which is almost all shales and thoroughly bioturbated by insects and other things. So this is a map from a 2004 publication that shows that there's some marine deposits up here, but this is just the Saltwash. This is just a map of the Saltwash. And we're going to look at this area in more detail and then look at some outcrops. But in this area, well, let me just show you the details. So this is all river deposits. I'm going to show you the evidence for that in a minute. So this is a thickness map of the Saltwash, just this section in Utah and parts of Colorado and a little bit into Arizona and New Mexico. The arrows indicate the directions of flow of the water. So everything is flowing, generally from east to, or from west to kind of northeast, east-northeast, with some variation. And you can see how thick it is here. So that's 175 meters. So almost 200 meters. So that'd be, give or take 300 feet, 600 feet thick, 600 feet thick. And then thinning to the east. Now, there's kind of a lobe here that's forming. Within this lobe, say along those lines, and it's missing here because it's been eroded away, there are no marine fossils. So it's 300 to 600 feet thick and no marine fossils. It has been investigated. I mean, this is probably one of the most investigated units in the world for fossils, and no one's ever found a marine fossil. So this idea that, one of the ideas I want to dispel is that terrestrial fossils from the flood are always mixed with marine fossils. And they're not. In fact, the vast majority of terrestrial fossils are not mixed with marine fossils. So
now, are you saying that in none of the layers there's marine fossils, or are you saying in this one segment in the Morrison Formation there's no marine fossils?
I'm saying in this one segment in the Morrison Formation, from there to there, this one segment, which is 300 to 600 feet thick, there are no marine fossils anywhere. And in the Morrison Formation in general, there are marine fossils, but you have to go quite a distance to find them. They're not common, and they're not mixed with terrestrial fossils, or maybe they're mixed just a tiny bit. The vast majority of the Morrison does not have marine fossils. Now, in the area of Green River, like right here, this is I-70, just for reference. That's I-70. There's Grand Junction. This is Green River, Utah. So in this area in Green River, there are no marine fossils in the Brushy Formation, or the Brushy member, excuse me. So there are marine fossils in the Morrison, but just not in this area. You have to go quite a ways. to
Now,
get.
how do you see that in, your understanding of geology? Why are there marine fossils in so far inland? How did these marine fossils come in there?
Well, there was an ocean bay right here. Do you see where I'm pointing?
Yeah.
Yeah, that was a bay. And through time, that bay got bigger and it moved to the south. So there was a rise in sea level, but that doesn't impact this at all. None of this is marine. So, sea level is going up and down. When sea level goes up, it floods the continent. When sea level goes down, you get terrestrial deposits.
So are you saying that came all the way down to the Utah area, or are you saying there's no marine fossils in the Utah area?
There's marine fossils above this. So I stopped here. This is one of the big mega sequence boundaries right here. And that's Cretaceous. And I ran out of, didn't want to show it, but I'm going to show a picture of this deposit here. There's 2,000 feet of marine shale on top of this.
Okay. So there's lots of marine fossils. It's just not in that one section.
Not in this unit. Yeah, I want to make that clear. Not in this unit.
Okay. Do you think that's inconsistent with a flood, a worldwide flood?
Well, I'll show you the evidence and then you can answer that question. So one of the criticisms I've heard is if you look at modern erosional rates, the mountains would have long ago disappeared. And that's true. And the vast majority of mountain belts, in fact, have disappeared. They've been eroded. I shouldn't say disappeared, but they've been eroded away. So this is all this sediment that was being shed here. And this is, I did a quick calculation, 14,000 cubic kilometers of sediment in this one lobe. That sediment was being shed by mountains out here called the Sevier Mountains. Those mountains are gone. There's other mountains there, but those mountains are gone. They've been eroded away a long time ago. And so, all this sediment was being shed to the east. The Rockies didn't exist. The Rockies would be like Gunnison is in the Rockies. So the Rockies didn't exist at this time because the rivers are flowing right past them. So what we're going to do is we're going to zoom into this area right here and look at some outcrops right there. And this is, I've referenced some publications. I've worked on this a lot when I was with Exxon, but I haven't published on this. So here's one of the outcrops.
Quick, before we move on, how do you know that there were mountains there? That mountain range?
That's a good question. So there's several lines of evidence. First is the direction of flow of the rivers. So all the paleocurrents are indicating that you're going downhill to the east. So if you're going downhill to the east, you must be going uphill to the west. And then the huge volume of sediment that shed here, and that's 14,000 cubic kilometers is a lot. So that sediment had to be coming from the west. And there's structural and mineralogic data for the cores of the mountains. Now, this is not my specialty, but because of isostasy, if you have a mile-high mountain, or say, there's lots of 14,000 peakers, 14,000 foot peaks in the Rockies, right? So 14,000 is about 2 miles. 3 miles. I have to do my math. So if you have a 3 mile high mountain and you erode it down 3 miles, you still have a mountain because of isostasy, it pops up, very slowly, but it does pop up. So you have to erode down, and I meant to do the math before this conversation, but you have to erode down something like double that to get to the point where the mountains are gone because of isostasy. It's like if you eroded the top of an iceberg, well, the iceberg would just float higher in the water. And that happens with mountain chains too. And this is something we can measure today. And so by the time you erode the mountains to the point where they can't be eroded anymore, you're down so deep from what was there when the mountains were formed that you're looking at metamorphic rocks. And so we see the evidence in the metamorphic rocks and in the timing of structural deformation. And so in places there's the sediments are caught up in the structural deformation. So that gives you some relative timing. So that's how we know that the mountains were out here.
Okay, thank you.
So here's, so one of the comments I've heard, like the Morrison and all these deposition units, they go for hundreds of miles, which is true, but that doesn't indicate a global anything because the individual rock units don't go for hundreds of miles. So this is I-70. You can actually park just, this is we're looking more or less east. Excuse me. We're looking west towards Green River. This is in between, or excuse me, we're looking west towards the San Rafael Swell. We're about 10 or 11 kilometers west of Green River. I get east and west mixed up, so I have to go slowly here. So here's a sandstone body right there. And this is a photograph of that same sand. So that's where it ends. So the Morrison Formation does extend over a huge area, but the individual rock units don't. They're small. There are places further to the west where they're more amalgamated than this. So here you can see the base of this channel cutting down. It cuts out all of this. And so the best interpretation of this is all trough cross-bedded gravelly sand. And so the best interpretation of this that's consistent with all of the sedimentology is that this is the remains of a river channel. This is one of those river channels that's flowing to the east. And this is kind of a lengthwise cut through that. And then here's another one up here. And so, this is an outcrop you can go to. It's actually pretty safe. Just east of this is a big pull-off area where you can park and you can walk along this outcrop pretty safely. So you can access this easily. And then a short distance away is this. We were looking at this earlier. This is a unit that I worked on. We took this core right here. The Paleo currents indicate that the Paleo currents are going this way. So our interpretation is that this is a river channel. We've lost this end, we've lost this end, but this is a river channel. The sand is very thin here, and very thick in the middle. Somebody blasted through a little drainage ditch here, and so we're standing right here. And so there's actually a series of stack channels. Not all the sand has been broken up because it was blasted, but this is Paleosol shale. It's all bioturbated terrestrial shale. And here you can see one of the channels, and then here's another. There's a little kind of undercut here, and there's another channel. And this is all trough crossbeds. So we know from the trough crossbeds, the paleo currents are going almost due east. So that's downhill. We know from the scale of the crossbeds how deep the water was, and not that deep. So maybe the thickest crossbeds are about 1 meter, so maximum 20 meters deep, but far more likely to be about 6 or 7 meters deep. We know from the paleontology there's no hint of marine influence. We know from the shales that there's lots of insect bioturbation and soil features, so that the shales were soils. And so by far the best interpretation is that this is a river channel in the Jurassic and has nothing to do with marine deposits. And there's dinosaur bones in here, and there's hundreds of these features, maybe thousands. I don't know anybody that's counted them. And there's some publications on this, on these channels. Nobody's published this particular one, but there are publications of many of these features nearby. So hundreds and hundreds of these kinds of features. And some of them, this one's kind of straight. Some of them are more curvy, but they look like, modern rivers. And I'm trying to remember what the next slide. Oh yeah, there's a lot of dinosaur bones in here. This is from a few miles away. It's called, I don't know if you've ever been there, but there's a stop on I-70 called a Trail Through Time. And it's about a 1 mile walk, and it's through this unit. And you can see the individual channel sand bodies, and there's dinosaur bones. So I just took pictures of a few dinosaur bones in there. The vast majority of dinosaur bones in the Morrison are just small chunks of dinosaurs. You only rarely get complete dinosaurs. That's why I put this in here. And then there's a paper by Steve Hasiotis, 2004, where he goes into all the insect burrows in the Morrison soils. So a whole paper on just the insect burrows. And there's lots of different kinds of insect burrows. So this is one of my favorites. This is a dung beetle burrow. So you know what dung beetles are? They're the beetles that roll the bits of dung backwards across the soil surface. And so here's the dung ball, and there's the burrow. This is a termite burrow. So the top of the soil was up here, and this is a very distinctive style of burrowing by termites. And so since the burrow was open, water could permeate the burrows and cement it up preferentially. And there was soil around here. So these are, you can see them in the outcrop, but the soil has been eroded away. So you just see the burrow that's underground. But these are, I don't know, 5 foot high. There's a pen for scale right there, like 5 foot high burrowed network. This is a network of burrows. And this is from that same core I showed earlier, and it's all completely bioturbated, but it's bioturbated by insects. It's all insect bioturbation. So there's 2 papers on this. Hasiotis 2004 as just Morrison formation ichnofossils, and it's mostly insects. And then Tim Demko has published on the soils in the Morrison formation. So, when you look at all the evidence together, it just, I don't know how you can escape this being a river system, and the level of maturity of the soils and the amount of insect bioturbation. Tim Demko estimated that some of the soils took 1,000 years to form at least. So you've got, I don't know if he was right about that. I think more work suggests maybe hundreds of years for some of the soils, but you need thousands of years for the stacks of soils to form. I don't know how you can escape that. And I've heard some of the criticisms against interpreting paleosols. So Michael Ord had several. He has a recent publication on I forget what website it's on, but he has a publication on a website. And so he has several criticisms. One is he said that most soils in the ancient are missing the organic enriched horizon, which is present in most modern soils, but it's not. Most modern soils don't have an organic enriched horizon. He said that horizonation, which is the process that produces the horizons in soils, there's 3 mechanisms that produce soils. One is biologic, which is all the insect burrows and rooting. The second is chemical. So rainwater is just slightly acidic. And so over thousands of years, as it permeates through the soil, that acidity changes the chemistry of the minerals and will dissolve some minerals and redeposit them deeper down. And then there's mechanical, which is wetting and drying. So when you wet the soils, the clay minerals expand. When you dry them, they contract. And as they slip past each other, when they do this repeatedly, you get distinct structures. So, yeah, I don't know that I could go through all the different criticisms of why creationists don't like soils, but none of them that I've heard hold up. One of them is that there are hydrothermal alteration products that look like soils, which is true, but they form around hydrothermal vents. They don't form layers that are horizontal for hundreds of miles, and they don't form insect burrows. So it gets tough, I think, to get around the soils. And so I'm not going to, this is it. I think this is it for the Morrison. We're going to go to the Cretaceous now.
Okay, but I want to ask about the soils
Sure.
because, I have heard these responses about the soils, and it seems like a very good response to me where there's the criticism of, well, but most of what we see in the Earth's sedimentation is not soils. It's sediment upon sediment. So if it really has been, all of these cycles, where are those soils? Why don't we see those soils? Why do we have sediment layer and no soil there and no evidence of erosion in a lot of layers?
First, what you said is correct, that most layers don't have soils. But in the Morrison, it's soils top to bottom. I mean, they're just in the only places that don't have soils that I've seen in the Green River area in much of that part of Utah is where you have the river channels. Those are sand, but other than that, on top and below them, you have soils. But there are other deposits that don't. And so I'm going to hold off on that question until we get to the Cretaceous, which is next. And we're going to look in detail at that, of where the soils are and where the other strata are. Is that okay?
Yep.
Okay. So I think we've covered this. I've just shown one example in this area, but there's, lots and lots of outcrop here. And there's many publications on this that talk about the distribution of these soil horizons and the distribution of the river channels and the severe mountains. There's lots of, publications on the severe mountains. Okay, I just threw this in because I thought it was a cool picture. This is another exhumed river channel in the Cretaceous now. This is sitting on one of the mega sequence boundaries. So the idea is that this is sandstone filled, and the shale that was around here has been eroded away, leaving just the sandstone body. This sandstone body is 6 kilometers long. So what's that, about 4 miles or so? There's a road for scale. So I actually flew over this in a helicopter when I was doing field work for Exxon, and I had put my camera down between my feet while I tightened my seatbelt, and then the seatbelt automatically tightened and I couldn't reach my camera, so I couldn't take this photograph. So Tim Demko took this photograph and I got it from him. But there's a publication on this. This publication's on this feature. So now we're moving to the Cretaceous. And so here's a picture of the marine shale. There's 2,000 feet of shale. The Morrison is below my feet here, but you can just go downhill and you can find the Morrison formation. And so here's now a paleogeographic map of the Cretaceous. And here's Utah. We're going to look at Utah. We're standing right there. And so there's this big, thick marine shale unit that extends basically from the Gulf of Mexico all the way up to the Arctic. I mean, it's just a huge deposit. The Rocky Mountains would have been right here, so they weren't present at this time, but there were mountains further to the west. This is the same severe mountain belt. And this is, highly artistic. We know there's mountains there, but whether they look like this, I mean, who knows? But the Seaway, the coast of the Seaway is not artistic. That we can map in great detail, and I'm going to show you how we do that. So we're going to look at this area right here, which is right near here. And I think the next one's a cross section. Well, no, the next one's an example of a river valley. So this is Tusher Canyon. There's the lat long. You can drive there. It's from Green River. You need a vehicle that's an SUV with good clearance, but you don't need 4-wheel drive. I've been to this outcrop, 20, 30 times. And so here's another example of incision. So there's an incision right there. And so here's my illustration of that. There's a person for scale right there. So these, in this case, there's no limestones in here, but we do have marine sandstone. So this is a marine sandstone in light yellow. This is another marine sandstone in light yellow here. And then there's a marine shale here, which it's mostly in shadow, but it's right there. That's the marine shale. And so we know these are marine from marine fossils and marine burrows. Then there's an erosional surface. It's kind of hard to see this one, but it's really easy to see this erosional surface. And so you can see it cutting down. So it cuts out the marine beds. And then within this, the sedimentology is completely different. In the marine beds, there are these sedimentary structures called hummocky cross-stratification. I'm not going to go into what that is, but it's formed by waves just offshore of a beach. So, maybe a mile offshore of a beach, you have waves impinging on the bottom and they form hummocky cross-stratification. Within the incision, it's trough cross beds and current ripples and plant fossils. So it's all terrestrial. So here it's all marine fossils. Here it's all terrestrial fossils and completely different sedimentology. And you see a nice incision. And that nice incision is right there. And then it comes up on the other side, but there's talus here, so you can't see it. And so we're going to look at a cross bed. So this is a cross bed. So this is another example of trough cross bedding. There's my knife for scale. This is about a little less than 0.5 meter thick. And so on average, maybe 3 meters of water maximum, maybe 10 meters of water maximum. We know it was flowing. If you do the paleo-currents on this, it's flowing more or less to the east. So it's going downhill to the east. And these marine beds were probably under 20 to 30 meters of water. So sea level had to go down in order for these rivers to erode this valley. I just want to point out, there's a really good YouTube video that goes into far more detail about the sedimentology. And this is, it's called Dr. Antoine's Rockorama. And it's if you look at just the episode called Tusher Canyon. This is a really famous outcrop for petroleum geologists. I've taken hundreds of geologists there. I've actually met other petroleum geology groups at the same outcrop many times. And so it's not that incisions like this are very rare. What's rare is an incision like this that you can walk up to without having to climb or without having to, get in a precarious position. So just the other side of this rock down here, I've just trimmed it out as the road. So, you can drive up to this outcrop and park and walk 20 feet and you put your fingers on the outcrop. So this is where I get to answer your question. So here's the book cliffs. This is I-70 again. There's I-70. There's Green River. There's Grand Junction. I forgot to draw the red line to the right there. And this is a series of outcrops, actually one continuous outcrop called the Book Cliffs. And this is a cross-section of just a small part of the Book Cliffs. So I want to describe what this is because this is going to directly answer your question about soils. So this is that big, thick marine shale that I photographed earlier is this, except we're just looking at the upper third of it or so. We're not looking at the whole thing. So this is marine shale. Everything in gray here is marine shale. We're looking at a cross-section that follows this purple line, right? And so you can walk out all these relationships. You can walk out. So this is marine shale, lots and lots of marine fossils in here, ammonites and microfossils, all sorts, and lots of bioturbation. And then the yellow are those hummocky beds that I just pointed out in the previous. These are marine sandstone beds with marine burrows in them. Everything that's green and red and black is terrestrial. The black are coals, and the red are individual river channels, but there's just so many of them, they just mush together in this cross-section. And then the green are soils. So to answer your question, what you asked before, it's like, why don't I see the soils? Well, if you were walking through this part of the section, you would see no soils because it's underwater the entire time. But if you were to walk through here, this part of the section, it's filled with soils. So it just depends on where you are at a particular moment in stratigraphic history. And the boundary between the yellow and the green is the shoreline. So there's the boundary, and you can see the shoreline kind of moving back and forth through time. Okay, so does that answer your question? This is why you get lots of soils some places and almost no soils other places. It depends on the stratigraphic history. And this is how we know where the shoreline was on that map we were just looking at. So, and that's also, it can't have been a worldwide flood because there's the shoreline. It's not worldwide. I mean, this is the coast. And in some places, the entire coast is preserved and you can just walk up to it and see the beach and you can see the offshore part of the beach. You can see roots. There's lots and lots of roots in this system. And so we know that there were plants growing. Notice how the coals are only on the left side of the shoreline in the green area, and there's lots and lots of other indications that the green is terrestrial. So there's tons and tons of river valleys river channels in here, I should say. These brown things are the river valleys. So you can see there's lots and lots of river valleys. So each of these river valleys formed, it's just like in Kansas. Sea level went down is the interpretation. And then the rivers eroded these incisions, like the one I just showed you, and it was filled with river sands, sometimes with some estuary. And then sea level went up, and you got widespread marine units up into the coast on the left. And then sea level went down, and you see this cycle repeated over and over again. So we were just looking at this one, and then I'll just go one more. So this is the one that we were just looking at. And then here's another one. This one is if you drive on I-70 and get off at Thompson Canyon, there's an outdoor museum, a petroglyph museum. There's no signs on I-70, which is unfortunate because it's a spectacular petroglyph site. And if you park at the petroglyph area, walk across the road, you see this outcrop. So these are marine hummocky beds here, part of an offshore part of a beach, probably 20, 30 meters of water. Here's the incision. And this is all trough cross beds, best interpreted as river deposits, deposited in maybe 5 meters of water or 6 meters of water, and it's all terrestrial. So this is all marine, this is all terrestrial. And so this one is this guy right here.
Yeah, and this kind of brings up for me, what do you think would cause all of a sudden we have like a bunch of terrestrial fossils, right? Like, so how did those all get fossilized?
Well, it depends on the type of fossil. Most of the dinosaur bones are just individual bones that possibly laid on the surface. I mean, bones last a long time. They last thousands of years. And so they get buried. Plant fossils, most of the plants you see in these deposits are just like individual leaves or branches. You see impressions of wood. And in this outcrop, if you go to the right and climb up, this is private property, but you can get permission to get on the property. You can see impressions of bark and things. So nothing spectacular.
So you're saying it was not due to water and sediments rapidly burying fossils.
It was due to water and sediments. So all this trough crossbeds is deposited by water, but the best interpretation is it was freshwater in rivers, not marine. And so sea level definitely had to come down to get from there to there. And so none of the fossils I've seen in these deposits require spectacularly rapid burial. They're mostly just bits and pieces of things, especially the plants. They're just like chunks of wood, maybe this long, not like entire trees. There may be upright trees in here someplace. I've never seen them. There certainly are upright trees in other places, but I've never seen them. I've been to lots of outcrops in this area, but it's too extensive to have seen everything. So I don't know of any evidences of spectacular preservation in this system.
Okay, but are you saying that above the red line, that was what period of time? How long did it take for those sediments to deposit?
That's a really good question and just about impossible to answer because there's no way to measure how much time that was. And so I wouldn't, individually, there's in freshwater systems, there's no bioturbation. So there's bioturbation in soils, there's bioturbation in marine sediments, but even in freshwater lakes where there's very slow deposition, there's no bioturbation. So we can't use bioturbation as a proxy for depositional rate. And so it's very hard to say how long this took, but for an individual trough crossbed set, maybe a few days for it to form. But you also see that there's a lot of incision, like you see an erosion surface coming down there, and you see another erosion surface coming down there. And so there's lots of, cut and fill, as we say, or cannibalization. So things get deposited, then eroded, then deposited, then eroded, then deposited, and eroded, and it just gradually fills up the valley. So I can't really answer your question in terms of a specific rate because there's no evidence for it. For the hummocky beds, it's very common where the top of the hummocky bed is preserved that's completely bioturbated. So there's time in between each of the hummocky beds. So you deposit a hummocky bed, it gets bioturbated. You deposit another one, the top gets bioturbated. And the depth of the bioturbation is commonly just a few inches. So maybe that took a few weeks for that to happen or a few months. It's really hard to put like a hard amount of time on it, but it does show episodic deposition.
But none of this that you're showing me on the photograph would need millions of years. Necessarily.
Yes, that's correct. But you do need, all this shale is bioturbated. So you need, I don't know how to, this is just 100 meters and the shale is 500 meters thick, something like that. And I've never sampled the whole thing, but I've seen lots of samples in places where it's bioturbated. So, the very minimum amount of time you would need just for the Cretaceous, if you ignored all the radiometric dates, would be, tens of thousands of years just to account for the bioturbation. I'm trying to think if there's any, just the intense bioturbation and the time for sea level to go down and then go back up and then go down and back up. The cycles here are commonly interpreted as tectonic cycles, so not the glacial eustatic cycles that we saw in the Pennsylvanian. I think that might be wrong. I think things are maybe changing, that maybe there was some glacial processes going on here. But the point is that that these are river valleys. I think that is pretty hard to get away from. These are river valleys. And so sea level went down, the rivers extended basinward as you expose the seafloor, and the rivers eroded valleys. And so all the sedimentology we have and all the paleontology says these are river valleys and these are marine deposits.
Okay. Now, when you say river valleys, I'm thinking of an entire ecosystem. It was once an ecosystem with grasses or plants and animals coming by and things like that. So is
Correct.
there evidence that this thing that you're pointing to and saying was a river valley? Is there evidence in that formation that shows that this was once an ecosystem?
Yes. So there's lots of plant fossils in here. Plant fossils are pretty easy to find. As you go,
I mean, are they in place as we would find if it was an ecosystem? Or because if you can deposit a plant anywhere, it doesn't mean that it was part of a ecosystem.
So there are lots of rooted horizons here. So that shows that the plants were living there. So I think that the plant fossils themselves are usually pretty beat up, but there's lots of rooted horizons. So the roots show that the plants were living there. Now it's pretty hard to look at a root and say what kind of plant it was, but there are lots of rooted horizons.
But in this thing above the red line, you're saying we have plant roots that show that those plants were there in place.
At the top of this exposure, if you climb to the top, there is a layer where you can see plant roots in place. Yes. And I've got photographs of it, but they're not in this presentation. Are they in here? Nope, they're not in here. So
Okay,
yeah, there are absolutely, and there's lots. If you follow these coals, a lot of these coals here have roots extending down from the coal. That's really common. And so there's lots of rooted horizons in here. I mean, at this scale, this is really crunched down in scale.
Right,
So
I understand.
You can't show the roots. But I've seen lots and lots of examples, and I have photographs of roots in this, from this very outcrop. I have photographs of roots, but I didn't put it in this presentation.
Well, and this is why it's hard for me, this geology topic is the hardest to deal with when I'm trying to figure out how to think about Earth's history, because we're talking about everything on Earth. It's just very hard to just capture what's going on. But I like it. Go ahead.
I totally get that. And, we were discussing earlier in email about, I was trying to simplify the presentation. You said, no, don't do that. Leave everything in. And I'm specifically trying not to be overwhelming. So I'm showing multiple examples of the same kind of thing. In this case, just river valleys. But we could do a whole other presentation where we were just looking at deltas or just looking at beaches. And so I'm stressing river valleys here because I have some really nice examples of different ages with different types of river systems. And so I'm trying to show some repetition here, that you have valleys cutting into marine beds that have terrestrial fossils and river deposits in them.
Yeah, and I like it that we have a picture of a specific rock formation, because this will help. I want to understand, if you can, tell me what you think the history of this rock is, because it's very hard for me to imagine that the top of this rock was once part of a river valley. So how is this rock still here? How long has this rock been here in this form? And those kind of questions, those kind of things are things I would like you to answer to the best of your ability.
Well, we're looking at a modern canyon. So when you drive up the road to this site, and I encourage people to go there, there's a nice parking area, and there's a little, there's a little bathroom, so to speak. And so, it's a nice place to go. And there's a nice exhibit of the petroglyphs there. And as I said, this is across the road. So we're in a modern canyon that has been eroded recently. and I don't know, I'm not a geomorphologist, so I can't tell you how long ago that canyon was eroded, but it's eroded into the Cretaceous, and this is part of the Book Cliffs. So this is a cliff right here. So this marine bed is this yellow unit there. So it extends seaward about 10 kilometers, and then there's shale that keeps on going for, all the way to Kansas. So that's how far the shale goes. So sea level had to be high enough when this hummocky bed was deposited to cover that whole area from here to Kansas. And the hummocky beds here, if you followed them to the east, no, to the west on this diagram, if you follow them to the west, they become beaches. So we have sedimentary evidence of them being a beach. There is on this outcrop, this is very schematic, but the valley actually comes up. Maybe it's up here, but if you go up in this outcrop, there is a place where you get to some very nice beach outcrops. And then, so sea level is very high to form the hummocky beds, and there's marine fossils in the hummocky beds. Then sea level is interpreted to have come down. I'm trying to be very careful about what's an interpretation and what's an observation. So the observation is that the sedimentology of the upper sandstone above the red line is deposited by currents flowing more or less to the east. So that means going downhill to the east. The water depth was low, much lower than the hummocky beds, and it was all fresh water according to the paleontology. There's no evidence of marine anything in there. And so the rivers then eroded the valley. Now you have to remember that at the time this happened, this wasn't rock, this was just loose sand. So when sea level fell, the rivers would have very easily eroded that loose sand to form the valley. And these valleys are a few kilometers wide, and they're filled with river channels. And so those river channels are transporting bits of, I've never seen dinosaur bone in here, but I wouldn't be surprised to see some. There's certainly dinosaurs in other parts of the system, and plant fragments. I mean, just bucket loads of plant fragments. Nothing to write home about, but lots of plant fragments. And then the valley fills up with sediment, and that's what this brown is here. And then as sea level comes up again, that entire river system is submerged, and you get a layer of either marine sand or marine shale on top of it. And then that cycle happens over and over again. So I'm not sure I answered your question, but I tried.
Well, you did your best, but it's hard to imagine, it's hard to envision all of this. And to me, when I look at this rock, of course, right now there's a red line through it, so it's hard for me to see, but if there's a definite layer there, but it looks like one thing. It's hard for me to imagine that that there's a definitive thing going on here. It feels to me like there's a better. Okay, there we go. Let me look at this. Okay, so but
and let me just say,
coloring of the sediments is the same.
right,
so
but if you
Yeah.
walk around the corner here, so you see this is a corner, you walk around the corner, you can climb up, you can put your finger on this surface.
Right.
And the two types of sandstone are completely different. This is hummocky sandstone with marine burrows,
Yeah.
and this is very fine upper. Then you cross this surface, it's all trough cross-bedded sandstone with plant fossils, and it's medium lower. So different grain size, different sedimentary structures, and different fossils.
Right. And so I'm not saying that it couldn't be, different. I'm not disagreeing with your interpretation. With your description, I'll say. But to me, when I look at it, it's still hard to imagine that this section has a very long history that was separated by time, because even though what you're saying is, I'm sure is true about the different types of things that are in each part of it, it still overall kind of gives the appearance that it shares a history, like do you see what I'm saying with the coloring and sort of the
yes,
formation, the way it looks?
yes. I think if you went there, you would see that's not true. I'm going to put the red line back.
Okay.
This is a classic unconformity. And this is, there's probably 20 meters or 30 meters of relief on this one surface. And here where I'm showing it, it is a sand on sand contact, but there's other places where you can track this and it's sand on shale. It cuts down through the underlying shale. And so, it's not just sand on sand. And as I said, the sedimentology, this is just exactly the same as the Pennsylvanian, except in the Pennsylvanian, the marine deposits were limestones. Here, the marine deposits are sands and shales, but it's the same concept. So I'm going to go back to display mode, but I wanted to take the red line away so you could see what the unadulterated photograph
Right.
looks like.
Thank you.
It looks straight.
Well, it's the same day for you all, but this is day 2 for me and Dr. Feldman, and we're back to continue with his presentation. Go ahead, Dr. Feldman.
Thanks, and thanks again for inviting me. I really appreciate the opportunity to show an alternative view. So I'm going to start by just reviewing for the audience. They just heard this, but I'm still going to review it, what we said, and then for us, it's a few days later. So reviewing part 1, the first thing I talked about is that biostratigraphy is not circular, and I went into all the reasons why that is true. I mean, I'm not going to say that no one has ever done any circular reasoning about stratigraphy because there's probably tens of thousands of publications, but it certainly isn't common, and it's not the standard. I've never seen an example. Second is there's no world view when interpreting sedimentary rocks for geologists. The only uniformitarian principles that we use is that the physics of the way sediment is transported hasn't changed. The strength of gravity hasn't changed. The viscosity of water and so forth hasn't changed. There's no other assumptions. Let me get my pointer out of the way. So, and then when you look at the sedimentology of the units that we find, such as I use trough cross-bedded sandstone, those place limits, physical limits on the conditions during which those were deposited. And what we see a lot of times with the valley fills that I talked about is those physical limits are what we commonly find in rivers, that you have flowing water of a certain depth, of a certain velocity, and the water's flowing at the kinds of speeds that we see today. It's not super deep, covering all the land. The sedimentology precludes that. And in fact, a lot of times the sedimentology precludes that the incision was not filled with water. It was only partly filled with water, so there had to be land then on either side of the valley. And we're going to look at some more examples of valleys shortly. And we showed that there are widespread marine deposits beneath every North American location with either dinosaur trackways or egg nests. And so the reason why these are important is because fossils can be transported, like a bone can be transported, but dinosaur tracks, footprints, and egg nests can't be transported. And so that means that every place we see dinosaurs that were actually living or at least alive while they were making those footprints, beneath that level is widespread marine deposits, which means how did the dinosaurs get there? And in some cases, the nearest end to those marine deposits would have been over 1,000 miles away. And so when did the dinosaurs in a creationist time frame, when would they have gotten there? They would have had to be running, 1,000 miles. To me, that doesn't make sense. We looked a lot at the Pennsylvanian in the Midwest, and there are approximately 50 cycles, give or take, of widespread marine deposits followed by soils and valley incision. And this is repeated multiple times. And in the valleys, we find the terrestrial fossils. We talked a little bit about how we know the age of this. The biostratigraphic age comes from the marine units that the incisions are cutting into. And so if there, for example, there was a rabbit found in one of these incisions of the Pennsylvanian, you can't just change the age because you found a rabbit, because it's constrained by the marine deposits that are above and below it. So you can't physically change what the biostratigraphic age is. And we also reviewed, I forgot to put this in here, that the ages of all the named time units like Cambrian, Ordovician, Silurian, Devonian, all that Cretaceous, that's always determined by biostratigraphy. It's not by radiometric dates. And in fact, those units were established over 100 years before there was any such thing as radiometric dates. I think the only exception that's not biostratigraphy is the iridium layer at the end of the Cretaceous. I think that's now, I may be wrong, but I think that's now the standard for the end of the Cretaceous. So it's not a biostratigraphic event. And then we looked at the Jurassic Morrison Formation in Colorado and Utah, which is dominated by river channels and soils, almost entirely without marine fossils. There are some marine fossils in the Morrison Formation, but typically they're not in the areas, in the volumes where we get the terrestrial fossils, like all the dinosaurs and such. And we saw that the paleosols have a diverse assemblage of insect burrows. And so that's important because it's direct evidence that it was not formed underwater, because there's no insects that burrow underwater. Okay, so we're going to continue on with the Cretaceous. And so I just wanted to show a cross-section that I didn't include last time. So here's a map of the Cretaceous of the Western Interior. These kinds of maps are widely reproduced, and there's a lot of artistic license in this. So, the mountains, like where exactly the mountains were, like individual peaks and so forth, is artistic license. But the location of the shoreline of the Cretaceous Seaway, that is not artistic. We can map that in great detail. And so we're going to look at a cross-section here on this red line. This is obviously Utah. And on the right is a photograph of an outcrop near Green River, Utah, just north of I-70, and this big, thick marine shale, about 2,000 feet of marine shale. That's this marine shale. So the Rocky Mountains would be here, and there's no evidence that there were mountains there. The mountains were further west. Now, these mountains are long gone. They've been eroded away, but we still see evidence of them. So here's that cross section.
You mentioned the Rocky Mountains. How and when would you say the Rocky Mountains formed?
Well, they formed after the Cretaceous. So the Seaway had already gone away, and the Mississippi River had been established, and the Rocky Mountains started rising. That is not a tectonic event I have a lot of expertise in, but it was definitely after the Cretaceous. So,
okay, but is there a good explanation for how those formed? Like, I mean, you may not have expertise in it, but like,
yeah, it's a tectonic. I think I know there's a plate tectonic explanation, and there's a subducting plate that is going beneath the western part of North America, and I think it has something to do with that. And I know this has been worked out in great detail. You're asking me a question I didn't prepare for, and so I can't answer it. But what I can say is that the marine shale, which records offshore marine conditions, extends across the Rocky Mountains. Now, it's not preserved everywhere because someplace the mountains have uplifted and it's been eroded away. But wherever we see it, and it goes all the way to Kansas. And
okay, and I do want to say the reason I brought that up is because in between the time that we last met, I read most of this book, Carved in Stone. Have you read this?
Oh yeah, I've got a copy right here.
Oh wow. Okay. Interesting. So, and that's he talks about that, the Rocky Mountains, there really is not a good explanation in, the secular view of geology on how the Rocky Mountains formed.
I don't think that's true, but as I said, if you want me to investigate this, I can. It's just not. There's YouTube videos on the formation of the Rocky Mountains, and the only reason I'm hesitant is not that I'm trying to hide anything. It's just not a question I prepared for.
Yeah, no,
So,
I understand. And the other thing I did in between the time we last talked is that I talked to somebody who has a PhD in geology, and I talked to him about some of the things that you were saying in your last presentation, and he actually agreed with you on the index fossils and the biostratigraphy. And so he said, yes, we do see that pattern across the whole world. We see the same ordering. There are localized ones that, there may be some localized examples of differences, but in general, we do see what you're talking about. He did actually have he was kind of confused about your claim about the dinosaurs having to run 1,000 miles, if the marine sediments were deposited, because what he said is that, basically these marine sediments, actually the fact that we have dinosaur footprints shows that those sediments were soft and were basically, if they hadn't been rapidly buried, they wouldn't be preserved today. So, like, for him, it wasn't really a problem that there were marine sediments below that, because he saw it as like, you know, uh, sediments with marine fossils getting deposited early on in the flood, and then, dinosaurs walking over those like mud that was still, and sediments that were still soft.
yeah, I don't quite follow that. The point I was making is that wherever we find dinosaur footprints and nests, so that we know that they were alive while they were there, as opposed to bones which can be transported, there are such widespread marine deposits below them. And when I say below them, it might be a kilometer below them. I mean, it might be a
Right.
long distance below them. That if you go to the ends of where those marine deposits were, assuming the dinosaurs weren't just swimming and treading water, you know, you have to go, in some cases, 1,000 miles to get to the point where there would be land that they could have come from. And so then how did they get to where they are? Like there's tons and tons of dinosaur footprints in Utah, and there's some in Alberta. And again, I'm talking about these areas because these are areas where I've done field work and I'm quite familiar with the rocks.
Right.
So that's the point about them being soft. There's nothing unique about preserving footprints. There are footprints that are forming today that are in soft sediment that get preserved and it gets turned to rock. So there's two different kinds of rock in the rock record in terms of preservation. So there's siliciclastics. We introduced that term last time, and that's sand, which turns into sandstone, mud, which turns into shale, and gravel, which turns into conglomerate when it's lithified. And none of those rocks really can form rapidly or at the surface, so they're always going to be soft at the surface. And then there's limestone, which is made of shells and carbonate. The chemical formula is CaCO3, so it's not a clastic rock, which is based on silica. And so those sediments can be turned into rock almost instantly. We don't really know how fast, but there are lots of examples of, say, modern bottles that have been incorporated, not just on the surface, but in part of the rock in limestone. So limestone forms extremely rapidly. And I showed you an example of a valley last time where there were chunks of limestone that had been eroded from valley walls in the valley. So we know limestone gets cemented very quickly. About it being soft, that, there's nothing, a point I'm going to make repeatedly is there's nothing, or I shouldn't say nothing because that's never true. There's very, very little that we see in the ancient, say in the Cretaceous, that we don't see happening today.
So
Almost.
where do you see footprints getting formed and like preserved today?
I've seen it. I've read about it in other places, but I've seen it in the Bahamas. There's, I don't have it in this presentation, but we saw footprints from Western boots that were in limestone in the Bahamas, and it was solid rock. Like if you hit it with a hammer, it would bounce off, and those were, Western style boots. I mean, not.
Okay.
I mean, it might have been from 100 years ago, but yeah, absolutely. And there's all sorts of fossils forming today. So, there's some environments like at the bottom of a deep lake where it's very expensive to investigate. So we don't really know what's happening there. But just about everything else we see happening today. Now, there are certainly things that happened in the past that we do not see happening today. For example, there are no, seaways that look like this anywhere in the world. Right. So we don't see that happening today. But if you look at the sedimentology of the deposits of the seaway, they look identical to things that are happening today. And there's certainly lots of fossils forming. We see footprints forming, raindrop imprints. I'm going to talk about a lot later on. And I showed several examples already. And so we see this happening today. When I was working in Kansas, we had examined a lot of tidal flats, and we went to the Bay of Fundy where the tidal flats, the mud had dried. We could actually split the layers and look at the different layers of mud. And the sedimentology of those surfaces was identical to the tidal flats we were working in rock in Kansas. So footprints, instead of reptile footprints, they were raccoon footprints. But footprints are footprints. So we all the features are the same. This is something that's really critical, is that there's nothing unique, or I shouldn't say nothing. There's very little unique. Of course, like the asteroid that hit at the end of the Cretaceous, the deposits from that there's nothing like that we see forming today. So that's.
Do you see big animals getting fossilized today?
Well, you certainly see big animals getting buried today. I mean, people are finding like mastodons and mammoths, and in the La Brea tar pits in Los Angeles, there's all these thousands and thousands of skeletons that have been preserved. I don't know if you'd call that a fossil or not, but we see preservation like we see in the ancient. Yeah.
Okay. And do you see like massive amounts of sediment, like one massive amount of sediment that has like fossils of different types, like marine and terrestrial?
There are very few places in the world where you see marine and terrestrial mixed. Almost always, not always, but almost always, the terrestrial fossils are preserved in one area, and the marine fossils are preserved in another area. And there might be a small zone in between where you get the mix. There are some very big exceptions.
Wait, you're talking about forming today, or you're talking about in the stratigraphic record?
In the stratigraphic record. So very rarely are terrestrial fossils like one occasionally, but I mean like lots of terrestrial fossils. Very rarely do you find lots of terrestrial fossils mixed with marine fossils. It does happen, but it's not common. A huge exception to that, where you do see a lot of them mixed together, is the Solnhofen limestone in Bavaria. So it's Jurassic in Bavaria. I used to be up on how exactly that was interpreted to have formed. I think the best explanation is that it's some sort of large lagoon, and it's a limestone, but it's a mud limestone. So it's the equivalent of mud, but it's not classic mud, it's carbonate mud, which sets up very fast. But there's even there, where the preservation is spectacular. You have to realize that what you see in museums is biased, right? Nobody is, the average fish fossil is a single tooth. That's the typical fish fossil. But nobody's going to go to a museum where you have room after room after room of isolated fossil teeth. What people want to see is the nice, complete fossils. But those complete fossils are exceedingly rare compared to the bits and pieces. And so you get a biased view that you see all this evidence when you go to a rock shop, or you go to a museum. You see all this, hundreds of specimens of all these beautifully rapidly buried organisms. Yeah, but those are the exceptions, and that's what makes it into the museum. I mean, nobody goes into the museum to see a typical diamond, which is small and only good for industrial use. You go to the museum to see the Hope diamond, but there's only one of those. So you can't take museum specimens. They're typical of the life that was preserved, but they're not typical of the style of preservation. So even in the Solnhofen limestone, which is known for its spectacular preservation, most of the so I was in this Solnhofen limestone in Bavaria in a museum on a field trip years and years ago, and I was talking to a preparator, the guys that are hired to actually, take the fish fossil and make it look nice for a museum display. You have to chip away at the little bits of rock that are covering the fish. And what he told me was that almost always, whenever they have a choice, they want to excavate the bottom of the fish, not the top, because the top gets messed up. And so what that means is that when the fish landed on the seafloor, it sat there for a while, and the top got either scavenged, or it rotted so that small currents could then distribute the scales. But the bottom of the fish was embedded in the sediment, even if it's just that deep, with the fish on top of it. And so they would always, if they could, excavate from the bottom up and then turn that, and that's the part you would see in the museum. So there was tons of evidence that these fossils, these fish, sat on the seafloor for some time before they were buried, but not always. Sometimes the burial, like where you see a fish in the middle of eating another fish, that was obviously rapid. But most of the fish weren't like that. Now, what's really unfortunate is nobody has really collected data on what are the proportions.
The thing that comes to my mind, though, is when I think about when fish die, right? Like I've had a fish die in my aquarium, and what does it do? It floats to the top. It
Yeah, I know.
doesn't go sink at the bottom. So when you're describing things getting buried in sediment, I'm thinking, and the bottom part is in the sediment and the top is exposed. That makes me think of, maybe like a large mass of sediment that's put, carrying fish along. And then the mud is covering the bottom of the fish, but then the tops are exposed. And don't we find it's not just one little fish, in the it's like a bunch of fish, right? Like often more than one fish. So doesn't
Yes.
that kind of
Well, yeah. Well, there are clearly special conditions that are needed to preserve articulated fossil fish, and when those conditions are met, you get a lot of them. And so the Green River Formation has, who knows how many fossil fish have been collected, because there's no record keeping really, because there's commercial quarries in the Green River Formation in Utah. But I read online there's estimates of upwards of 1 million fossil fish have been, harvested from the Green River Formation. Most of them are just sold in rock shops, so there's no real way to count. But that's so incredibly rare. I mean, those kinds of deposits are world renowned because they're so special. The vast majority of sedimentary strata have no well-preserved fossil fish. You just find a bone or a scale or a tooth here and there. And so these are unusual, and that's why you see them in museums, because they're so unusual.
I don't know. I mean, my understanding is that we have several billion fossils that we've found, right? And yes, a lot of them are fragmented, but we have enough complete ones that we can say we have thousands of complete fossils of many species.
Yes, but they tend to be very narrow windows in the stratigraphic record. And so, for example, in those, valleys that we were looking at last time in the Pennsylvanian, there are some, and I didn't show them, but there are some, articulated skeletons of extinct animals, Pelycosaurus and such, in those valleys. But outside of the valley, there's none. And so because I worked in the Kansas survey for several years, I know a lot about Kansas geology. So there was one deposit we worked in, another valley that it wasn't one that I showed you, but another valley, and it had reptiles and those huge dragonflies and cockroaches and fish, but it was a small deposit, maybe 300, 200, 300 feet wide. And if you step 1 foot outside of that, there were no more fossil fish. So within that tiny deposit, there were lots and lots of fossil fish. I can't tell you how many I found. I headed up it was my grant. I was the PI on the grant, and we did an excavation of that deposit. And I can't tell you how many fossil fish I found, but in all of Kansas, there's that one place that has those kinds of fossil fish in that incredible preservation. And that's for the entire state of Kansas, for all the Pennsylvania. I mean, and so you have these very small windows, but when you get the right conditions, yes, you get lots and lots of fossil fish, but they're not evenly distributed through the rock record. So an analogy might be, if you went on vacation and you had, imagine you had a high resolution camera and you're going skiing and you took a picture at the bottom of the mountain and where everybody's getting ready to go skiing, and then you took a picture at the top of the mountain, and then you took a picture at the bottom again. Yeah, each of those pictures is super high resolution, but you can't actually put them together to make a movie. You don't know what's happening in between if all you had was the pictures. You can say, well, those pictures have thousands and thousands, millions of pixels. Surely that's enough. But it isn't. And so, I worked a deposit in the Mississippian called the Bear Gulch Limestone in Montana. It's Mississippian in age. And it has like thousands of fossil fish. I mean, just gorgeous fossil fish. And it had some terrestrial animals as well, insects. We never found a vertebrate, but we found some insects and occasionally a plant fossil. But as far as I know, and I'm going to say this and then somebody will come up with a counterexample, but I think I'm right, that for the entire Mississippi and North America, that's it. That's the only place where you get more than like one or two fossil fish is there's one deposit in Montana. And so, yeah, if you just look at the pure numbers of fossil fish, you say, well, how can we not have complete, evolutionary successions just based on the pure numbers? But they're not evenly distributed. If those pure numbers were evenly distributed, like every lamina, we had another fossil fish, yeah, you could put together a really nice record. It would be like a movie. But it's more like there are snapshots over very short periods of time in very small areas where you get lots and lots of evidence and then nothing, for a long time until you get another special deposit. The name for these in the geologic literature is called Lagerstätten. It's a German term that means mother lode, and it's where you get spectacular preservation. But the spectacular preservation is unusual. That's what you see in museums because that's what they want to show, because nobody's going to go to a museum to see the regular stuff. But that's not typical by any means. The vast majority of rock, like 99.9% of sedimentary rocks, do not have articulated fossils.
Okay, well, I think I have more to say on that issue, but I don't want to derail your presentation, so maybe we can talk about it at the end. So I'll let you.
So we're going to look at this cross-section of the red line right there. And so this is it. This is from an old presentation from publication from 1966 that I've highly modified and sketched. So this is a cross section that goes from Thistle and Price, Utah, down to Green River, Utah, across the Utah-Colorado border, and ends at Palisade. This is just before you're getting into the Rocky Mountains. And so what's nice about this area is there's been very little tectonic movement. And so the strata are more or less still flat. And so they're exposed in the book Cliffs, a series of cliffs. Here's a scale here. It's been dated on this one surface right there, that red surface. So everything is flattened relative to that, but the thicknesses are correct. And so this is 8,000 feet below the surface and 2,000 feet above it, or you can do kilometers here. And we're looking at, I should have put a bar here because this is really, we're actually looking at, I did this wrong. This is the entire Cretaceous. We're looking at the entire Cretaceous here. So the Morrison Formation is actually the Jurassic. That's this unit down here. That's the Morrison Formation. We were looking at that. And then this is all the Cretaceous. This is the red line here is a mega sequence boundary. And so Dr. Tim Clary has done a lot on mega sequence. If you read that book, Carved in Stone, you saw a lot about the mega sequence boundary. So this is so if you go to Green River, Utah, you can see that mega sequence boundary. You could, if you're willing to hike up like about 300 feet, you can put your finger on it. I don't know of any place along I-70 where it's exposed. I think it's mostly covered, but there are places where you can certainly put your finger on it. So the colors here are, wherever it's orange is fluvial, sorry. Sometimes I have to use the terms I grew up with, but that means it's river channels. Fluvial means river channels. And we went last time through all the evidence of why those are river channels. And we looked at some on I-70, some road cuts. Then the gray is marine shale. Yellow is coastal facies, coastal deposits in sandstone. And then green is soils, coals, and a few river channels. Then orange is river channels again. Red is conglomerates, just coarse-grained river channels. And so the point of this cross-section is this is the entire Cretaceous. Okay, I may be missing a tiny bit on the top, but basically it's the entire. So you see this marine, and this marine shale extends all the way to Kansas. So, that's how wide the seaway was. The point is we see the coast. The coast is at the transition from yellow to green. That's where the coast was. And so to the left side of that boundary is only terrestrial fossils. There's a little bit of mixing in the middle. And then to the right, going east, is only marine fossils. So like the shale, the Manco Shale has beautiful ammonites and all sorts of marine fossils in it. Occasionally you get a bit of plant, like a waterlogged log, but not very often. And so again, there's not really much mixing. There's a little bit right at the boundary, but the other point is we know where the shoreline was, and we've got both the sedimentology and the paleontology and the roots and the soils and the coals to show it. And so there's no point in time in the Cretaceous where everything was covered with water. We can see the shoreline, and all the paleocurrents from the river channels are going almost due east, which means you're going downhill to the east to the shoreline, and you're going uphill to the west, and then there's mountains further to the west, and those mountains have largely been eroded away. So we see the cores of the mountains, and we see all the sediment that's being shed. And the volume of sediment is huge. If you looked at the entire seaway up and down, I haven't done the calculation, but I'm sure it's going to be millions of cubic miles of, or maybe a million cubic miles. So we're going to look.
Can I ask though, what is below that? Like what sediment layers are below that and what's in them?
Sure. So below this is the Entrada Formation, which is one of these Aeolian units. And I know there's a lot of, creationist discussion about this, but I've looked at the Entrada quite a bit, and it's got sedimentary features that are unique to Aeolian deposition of sand that don't form underwater. And then below that, it's the Entrada, and then below that is the Wingate and then the Navajo. I may have the Wingate and Navajo confused. And there's the Chin-Lee in the Triassic. And if you go down far enough, is Devonian, widespread Devonian marine deposits, and then widespread Mississippian marine deposits. And then eventually it's the same stratigraphic succession, or very similar to what you find in the Grand Canyon.
Okay, so below this, you're saying that because you said there's marine sediments, but what kind of like fossils are found below this?
Well, if you go far in the Aeolian units, like the Entrada, Wingate, and Navajo, there aren't very many fossils. Fossils typically don't form very well in sandstone, especially shells. They tend to get dissolved. But I don't know specifically what's in the Wingate, Entrada. I've never seen any like leaf imprints or anything in those areas. I know very rarely there are some footprints in those units, but I've never seen any. And then below that is you're asking me questions I haven't really prepared for, but I was teaching this in the field just last summer.
That's
so
okay. Yeah, I don't expect you to have the entire Earth sedimentation memorized.
Yeah, so it's the Chin-Lee Formation below that, which is Triassic. And there are some in the Chin-Lee, there's some great crayfish burrows in the Chin-Lee that I took a class there just recently. And then the classes I teach are for petroleum geologists. And then if you go down far enough, it's Devonian, and it's Devonian marine fossils. And so this is the Devonian, I think, is exposed in the San Rafael Swell. So this is an uplift. If you go west from Green River, you drive over it, and there are canyons that you can go down, and you can see the Devonian down there and the Ordovician. And so, I don't know specifically what fossils are in there, but they're like marine shells. So it's going to be very likely brachiopods and bryozoans and clams and snails and other marine fossils.
Okay, so if I think about that as like below that as a shallow sea that was, covered in sediment, and then this above that, like, what would be the problem with interpreting this as a temporary seashore that was, later covered up?
That sounds good to me.
Okay, so there's no like need to make this part that you're showing, like it doesn't need millions of years for it, like there's no sign, there's no anything that it was like this for millions of years.
Well, I don't agree with that, because we have all the soils, and soils take time to form. Most of the coals that are in this region are rooted, and so that means the plants were living there, so that takes time. Wherever I've seen the Mancos cored, so the oil companies, Exxon and Shell, took a whole series of cores in this transition system here, and wherever they cored and those cores are now public. They're not necessarily easy to get to, but they are public. Both Shell and Exxon did, and wherever they cored the Mancos here, this is the Mancos Shale, it's completely bioturbated. Almost everywhere. I shouldn't say everywhere. There's always exceptions, but almost everywhere it's bioturbated. So that requires time. So I can't put a hard number on it, but you can't do it in a year, or you can't do it in 1,000 years. I don't think you can do it in 100,000 years. It's not enough time to form the roots and the soils and the bioturbation.
So how long are you saying it takes to do bioturbation?
Well, it's not just time, it's also thickness. So remember, we discussed this, that very few burrowers, very few burrowing organisms in marine settings. This is assuming that everything is ideal. We have well oxygenated water, and there's lots of nutrients, and the water isn't very turbid, all the ideal conditions for life. They will only burrow down about a meter, 3 feet. So if you have a really thick bed, doesn't matter how much time you have, the bottom, if the bed is 20 feet thick, the bottom is not getting bioturbated. Even if you let it sit in the seafloor 1,000 years, it's not getting bioturbated. So the fact that we have successions where hundreds of feet are just thoroughly bioturbated means you had to deposit a little bit, let it get bioturbated, deposit a little bit, let it get bioturbated. And then typically all the bedding or nearly all the bedding is destroyed. So, it's very hard to put a hard number on that, but we can say very confidently it took, to get thorough bioturbation down to about 3 feet takes a few months to a few years, depending on the conditions. And if you have 100 feet of that, you can do it in kind of 3-foot elements. So you just can't do it in less than a year.
Okay.
Yep. So we're going to look at just that red box next in more detail. So here's, we looked at this cross section last time. This is the Mancos Shale. This doesn't go quite as far east. There's the Utah-Colorado border, and it's not labeled here, but Price, Utah is about there. And so all this green and red, the red are fluvial channels, and the green are soils and coals. The black are the coals here. And then the yellow is the coastal sands, and then gray is marine shale. So the marine shale is full of marine fossils. And then we looked at some of these incisions, and I just want to point out the levels. So you got a small incision there. We interpreted all these as valleys. There's some disagreement on that, but most people interpret these as valleys. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, maybe 13, 14, 15, 16 levels, stratigraphic levels, where you have valleys incised into marine sandstones and shales. And so each of those, sea level would go down, you do the incision, sea level comes back up, you cover it with a sheet of marine sediment, sea level goes down, you do the incision again. And again, we can see where the shoreline is. And remember, in the Devonian, all of this was underwater because we have widespread Devonian, both limestones and shales. So this was all entirely underwater earlier.
What do you see as the mechanism that puts so many things underwater? Like, because it seems like that's what's happening all over the world when we talk about sediments. So what do you see as the mechanism for bringing that much water, that like large amounts of water shaped so much of the earth?
Well, I can't speak to every time, but I can speak to this time. So this is when North America and South America are splitting away from Europe and Africa. So they were together and they started splitting apart. And the mid-Atlantic ridge, the rate at which they were splitting apart, you have to use radiometric dates for this, but the rate at which they were splitting apart was very fast. And so the mid-Atlantic ridge went up as you have all those volcanoes that are creating new oceanic crust. And so the volume of the earth is constant. So if one part is going up, something else has to go down. And so all over the world, we see a marine incursion, not over the entire continent, but over large areas. Like only maybe a third of North America was flooded at this time. But all over the world, we see an increase in sea level at that time, and it's interpreted to have been a result of exceptionally active seafloor spreading at that time. And so as the mountains and the oceans went up and the continents went down, the ocean then covered parts of the continent. So we see this in various continents around the world. I'm just not as I can't speak to specific examples in other continents because I'm just not as familiar, but I do know this is a worldwide transgression, which means rising sea level. So does
And
that
do you
answer your...
see that time period as like the time period that would have formed a certain mega sequence or multiple mega sequences?
This is part of a mega sequence, yeah.
Mhm.
So when I was an undergraduate taking historical geology in 1978, I think 77, 78. We had to memorize all the mega sequences. So it's the Sa, Tippecanoe, Kaskaskia, Absaroka, Zuni, Tea House. I still know them. See, I can't tell you exactly where the boundaries are, but I still know the names because we had to, that was on the exams where we had to memorize them. Among professional geologists, we don't talk about them very much because we're mainly looking at finer detail. And so here's a couple incisions that we looked at. So this is one of the valleys. Here's another one. It's sand on sand, but the sedimentology and grain size of these two sands is entirely different. These are hummocky sands. I'm going to talk about them later, that formed by waves in beaches and have marine fossils. These are trough crossbeds that form from unidirectional current that we interpreted to be from rivers with terrestrial fossils. And so this incision here, which you can, you can walk right up to this. You can drive right up to this outcrop. It's, if you type Thompson Canyon petroglyph site into Google, you'll find it. It's not too far from I-70. And that's this guy right here. And then this incision right here is that guy right there.
Okay, I'm glad you put this back up because like I wanted to ask one more question about it.
Sure.
Because so what's confusing is, this is like above surface, right? And so, but this you're saying was once a deep valley. So are you saying like the rest of the rocks that were part of it all eroded down and this stayed, or like how did this get to be here?
Well, the Book Cliffs have all sorts of canyons eroded into them. And so there's a interesting geomorphology question about how that happened, but there were the rivers today aren't capable of doing that, but there were rivers in the past that were. And so these are modern canyons that have eroded back into the Book Cliff. So all this was, by the end of the Cretaceous, all this was completely covered in underground. And then it's after the Cretaceous that there's been erosion into these areas. So
in what way, like what would cause it to erode around all sides, but like leave this rock here?
well, but it could have left the rock anywhere. These incisions are so common that it doesn't matter what rock was left behind. It's not this specific rock. It's any rock at this level. If it was left behind, we'd see these incisions. So it's not, there's nothing particularly special about this location or this rock type. So right. You can see.
I'm just look, and this might be a stupid question, like because
no, there's no such thing.
Okay, but like, so when I hear these stories about like, okay, and I've seen this a lot where like there's these massive formations that were once like that, like they'll be said that there's like was once rocks around them, like that. But what process would get rid of all the surrounding rock and leave this?
Well, this is a canyon. So there's so this is a canyon, and so it's a narrow canyon. So when you're driving down the road, there's a cliff on either side. All right. So it's mostly rock. There's just a little bit where the canyon is. And so there's rock on either side, and we're looking at this outcrop, but to the left of us is another outcrop where the same feature continues. You can see it on the other side. So
okay, so are you saying this is like a matter of like we had to build a road, so we like exploded through it, or what?
No. There's nothing.
Okay.
This was a road that was built down the axis of a canyon, down the center of a canyon. So the road is here. Let me see if I can bring this up on Google Maps. So, I mean, this is vertically exaggerated, right?
Okay.
There's a
I
cliff
see.
on either side, and here's the
Yes.
road, and this is what we're looking at. Now, this isn't the exact location. It's actually, yeah, it's further up the canyon. But you see, we're just looking at a narrow
Okay.
little canyon with a road
Yeah.
down the middle.
Okay,
Right?
it makes a lot more sense now. I
Yeah.
think the blue sky in the background kind of made it look like it was a standalone rock.
No, it's part of a
Okay.
very long cliff.
Okay. Got it.
Okay, so you see blue sky in the background because I'm standing in the ground looking up.
Okay. I
Okay,
see.
this is a tall cliff. That's 30 feet.
Okay.
Okay. So now we're going to go to Alberta. I worked in Alberta quite a bit. This is the publication. I'm second author. Again, green, this is looking at a north-south cross-section. Green is soils and river valleys. Yellow is coastal. Gray is marine shale. And you have all these incisions. Okay, lots and lots of them. We're going to look at a few as an example. So here's, we're now in the late Cretaceous. So this is seismic. So let me explain what seismic is. This is the standard tool of petroleum geologists. And this is a petroleum data set that I was working while I was in Exxon. And the reason I can show this is because we published it. So most of the work I did, we can't show. So everyone is familiar with a sonogram, like a medical sonogram. Everyone has seen a sonogram of a growing baby inside a pregnant woman, right? Everybody's seen that. And what they do is they put a device on the skin and it projects sound waves, very high pitched sound waves into the skin, and then the sound waves bounce back, and that can be, with some very sophisticated software and hardware, can be converted into an image. We're doing the same thing here, except instead of a little sonic device, we're using dynamite. And dynamite produces sound waves which go down, bounce off the different layers, and then with sophisticated hardware and software, we can produce an image. So the way I've colored this, I made this image for the publication, is all these reds and yellows are sands and the grays are shales. So I've tried to kind of color it the standard way we're coloring everything. Now, there's 50 meters. So, we don't get the resolution that you would get in a photograph. The smallest beds we can see are maybe, 15, 20 feet thick for us to see it. But these continuous layers like this one, and this one with the green dots, those are all hummocky, cross-bedded sands, and we know this because there's tons of cores through this. And then notice this sand stops right there, and then it picks up on the other side, and so this black line is a valley. And all of the sands in here have current ripples and trough crossbeds and plant fossils. So we've got marine burrows. I mean, you're not going to find a dinosaur in a core. And when I say this core, I should explain that too. So what a core is when they're drilling a well, they can use a circular bit that is hollow. And so you get a cylinder of rock coming out, and then you can split it in half and view the sedimentary structures. So again, it's the exact same pattern we saw in the outcrop. And except here, it's much deeper. So we're cutting through sand, then shale, then sand, then shale, then sand, then shale. All this shale is marine shale. And we've got a valley that's about a kilometer wide and maybe 50 meters deep. So that'd be 150 feet deep. And then you've got another one here. So we've got all of these, there's 20 valleys that we interpreted here. And for each one of them, we have a cross section like this. So we can map all these in 3 dimensions. So this is a project that I did, published it in 2010. Long time ago. So so this is another diagram I made for this publication. And here, instead of doing a cross section where we slice vertically through it, what I did is a horizontal section. So I'm looking at a bedding surface, And this is in seismic. And so look at all these river channels. Like here's one right here. Do you see where I'm pointing? See that red?
Yeah.
Yep. And then here it is here. I colored it blue here. So I just colored each one differently. And so here's another one here and another one coming down like that, which is this guy yellow coming down like that. And then let's see, this is another one right here. And this is why it just really, and I react badly sometimes when people say there's no river channels in the rock record. It's like, well, here, I mean, this one study, and we've got like 20 of them. I mean, it's just, they're so common, and the sedimentology is distinct that these are river channels and nothing else. I mean, you just can't.
Okay, what is it about these that makes these river channels and nothing else?
Well, first of all, the what's outside here is the hummocky beds with the marine burrows. And when we go in these channels, we see current structures, not wave structures. The current structures are trough crossbeds and current ripples. And because they're trough crossbeds, especially, that puts limits on how deep and how fast and what direction the water was flowing. So we know the water is flowing parallel to these incisions, in this case to the north, although we can't tell that from the core because it's not oriented. And so the physical sedimentology constrains the depositional conditions that you can't have the water deeper than the channel is in deep in its incision. So they just, all the observations, each one constrains the conditions to the point where there's nothing else left. Now there are a few of these incisions that has some estuarine, some brackish water influence, so we know we were near the coast. And the morphology of the sand bodies, which I'm going to get into in a little bit. So it's all the observations together just force this to be a river channel. And so, I've heard, both Dr. Werner and Dr. Clary say there's no river channels in the ancient. And I don't know how else to say it than they're wrong. I mean, it's not just that there's one example. There's like hundreds or thousands of published examples of river channels where the sedimentology and the paleontology and the soils, and we had roots in this system too that we saw core with roots. So it all constrains the possible range of conditions to the point where rivers are all that's left.
Okay, well, and I only know that creationist argument from you. I actually have not heard creationists making that argument, but I believe you when you say they do make the argument. I just haven't personally heard it. And
I sent you a link a while ago. I sent you a link to a video by Dr. Werner where he did make the statement.
Right. And I think I watched about 5 minutes of that and I saw him making the argument. But what I mean is I don't feel like it's a very common argument and I don't understand the argument. So I don't really have anything to say about it. I mean,
okay.
Well,
the thing is that each of these river channels takes time to form. So you need a river and you need time. And you need that amount of time for each one of these. And there's like dozens of them in this one area. So that's the argument. And so sea level has to be low to form these. It can't be above. The shoreline had to be a long ways from here. So let me go and look at a couple other examples. So, it's not. So I have heard Dr. Clary say this many times, and in his book, he never talks about river channels or soils in his book. He never once mentions them. It's not that he has an alternative interpretation. He just doesn't mention them, which I think is, you can judge for yourself what you think about that. But and he has said in videos, he's got lots and lots of interviews online, and he's said repeatedly that there's no river channels in the ancient. And so, in the Morrison, he said there's no river channels in the Morrison. And there's dozens of river channels that have been published, and there's hundreds more that have not. So
now, is it possible that they're interpreting these formations in a different way? Because I have heard a lot of talk about, we see like evidence of water like runoff. And so, this is an interpretation of various sediments and like different stages of the flood where water is moving. And then there's once sediments are, like one layer of sediments will be deposited, and then there's another time period where there's like sediments running off, where there's massive amounts of runoff.
Well, except that the sedimentology isn't consistent with that. The sedimentology is consistent with modern, the types of velocities of water and depth of water you find in modern rivers. So I don't think runoff forms different kinds of structures. I don't see how that would work. But, in one interview recently, just in the last, 6 months, 4 months, Dr. Clary said that he's never actually seen anything that looks like a river channel in the Morrison. And, I asked him, well, and he's been at places where it doesn't have river channels, but there's other places where it does. So I think it's more complicated than that. So here's an example of just a nice long one. This again is a seismic image. And so you see this river channel that is about 6 kilometers long. And here it is in cross section. So, so that's, I think that's pretty clear. And so it's not like there's just one. The point I'm trying to make is there's not just one of these. And so you have to have sea level going up to form these widespread marine deposits, and then sea level goes down and you get river channels cutting into them. Then sea level goes up, and you have to have this happen in the Cretaceous dozens of times. And so then the question is how, because you've got the shales are commonly completely bioturbated. So we know the marine deposits are slow. Depositional rates are slow. So I'm going to go, I just got a little bit more on rivers. So I want to go, it's not just that we see river channels in the ancient. There are 3 main kinds of rivers today: meandering, braided, and anastomosing. It doesn't matter if you don't know what those are, but the fact is that we see those 3 kinds of rivers in the ancient too. So it's not just that we see rivers, that we see specifically the kinds of rivers we see today. And so I wanted to show just one kind of river and show you what it looks like in the ancient. So this is called a meandering river. The Mississippi is an example of a meandering river. So it's sinuous. And as the river flows, the outside of the bend has higher velocity than the inside of the bend. So you get erosion on the outside of the bend and deposition on the inside of the bend. So you get deposition of sand here and erosion of whatever the sediment is out here. And so I'm using green with little plant symbols here to indicate that it's overbank. And so this is an example in the Mississippi River. There's the bend around it. This is colored by topography. This is a LiDAR image where you take an aircraft and you use reflected light and time how long the light takes to go down and come back up. And you can get topography that way, very, very detailed topography. And so, and all these scars that you see here, all these arcuate scars, that's the same as these right here that I've shown just very, very schematically here. And there's lots and lots of examples where this has been cored in the modern, and you've got an erosional scour at the base, and then you've got trough cross beds going up to current ripples and mud and a soil on top. And so if we look at this was a river channel in the Mississippi that was abandoned in, I think it was 1733. And what happens is as the outside of the bend erodes and the inside of the bend deposits, the meander loop gets longer and longer and longer and longer until it can't be sustained, and the river cuts a shortcut, which is this right here. So this is the modern Mississippi. So we've got a couple cores here that I'm showing schematically. One from this location where it shows that there's the bottom of the channel, coarse grained sand going up to finer grained sand, and this is trough cross bedded going up to current rippled, and then this is the abandoned channel fill, which fills with mud. Here's a map of the lower Cretaceous in Alberta showing, and these maps are at the same scale. So 1 kilometer on the left is 1 kilometer on the right. And this is seismic. So this is sitting at a mega sequence boundary. Below this unit is Devonian limestone, and above is the thick marine shales equivalent to the Mancos. And I've highlighted here in green the abandoned channel fills. There's one loop there, and there's another loop there. And you can see all the meander scars here. Do you see what I'm pointing to? See these arcs
Yes.
that go like that? Okay. So we know from modern rivers how fast those form. And you can get maybe up to about 40 meters a year. And so you need, to get this is maybe 5 kilometers long. So it'd be 5,000 divided by 50, that'd be 100 years. So, more than 100 years to form this point bar. And again, this is another one, more than 100 years to form that point bar. And when we look at the sedimentology of these deposits, it's not just similar to modern meandering rivers, it's identical in every way. There's no difference, except the fossils are different. You don't find dinosaur bones in the modern rivers. And so you need, to form these kinds of patterns with the sedimentology that we observe, you need hundreds of years. You can't do it in less. And if you have more water flowing through the system, you would just get a bigger river, which we don't have because we can see the width of the ancient river right here. And remember, this is marine deposits.
How far down is this?
In this case, it's probably about 300 or 400 meters below the surface. And that's all marine shale. So it's marine shale down to this level.
Okay, now, is there any reason that this couldn't be an underground spring?
Well, look at the scale here. That's a kilometer. So this is like 10 miles across. So what kind of spring is 10 miles across? I mean,
Well,
and this is thick. So this
I don't know much about underground springs.
Yeah. So this
I don't know.
This is about these deposits right here are about 30 meters. So that's say 100 feet thick. And this is all cross-bedded sandstone. So trough cross-bedded sandstone can't form underground. It just can't. So we know that this is, and there's soils associated with this. At the tops of the bars up here are soils. I've worked on some of these cores. I mean, they're public. All these cores are publicly available. And so there's soils. I mean, all the evidence that these were formed subaerially before they were covered by marine shale, and they're eroded into Devonian limestone.
Okay, this to me does sound like a good objection to the flood model. I would like to hear what the creationist response is to this. So has this been presented? Have you heard what the creationist response would be to this?
There is none. I've looked and looked. There is none. They don't even acknowledge this exists. And this was published in 2011. So it's not exactly recent. And this is why I've been asking, like, Standing for the Truth, Donnie Babinski, is that his last name? And, he initially agreed to let me have a debate, and then it was canceled and nothing since then. And, this is why you can't just present this in a YouTube comment, in a chat. You have to see the picture in order to understand what this is. So, and when we map the lower Cretaceous, I told you that was a mega sequence boundary, and you can see it outside of Green River, Utah. And you can, if you're willing to climb the steep slope, you can put your finger on it, and those are river deposits. And those river deposits were feeding into this. So when you map the entire lower Cretaceous, this river system was a Mississippi scale river system at that time, and it drained from about South Texas all the way, not South Texas, North Texas, all the way to the Arctic Ocean. So like 2/3 of North America was being drained by this river. It's exactly the same as the Mississippi, but mirror image. So the Mississippi is draining from the north to south. This was, when you look at all the paleocurrents, this was draining from the south to the north. And so, go ahead.
No, it's just, I keep hearing all these things that, okay, so what would cause that kind of, current and moving in maybe the opposite direction that the Mississippi River runs?
Well, so this is before the Mississippi, this is before the Cretaceous was flooded. So that big Western Interior Seaway that I showed before, this is just barely before that. And then after the Cretaceous ended and sea level went down again and you formed a new river system, you also had a huge tectonic movement because you formed the Rocky Mountains. And so all of North America is under stresses. And so that's the limit of my understanding of why it switched. But the fact that it switched is well documented. So it was a huge river system flowing north. And then after the Seaway came up, of course, there's no rivers underwater. So you had the Seaway come up that connected the Gulf of Mexico to the Arctic Ocean in one big long seaway. So no rivers flowing, underwater. And then when the sea level came down again, there were different tectonic forces. And so the drainage pattern switched. Okay. That's the limit. If you ask me any more questions, I'm going to claim ignorance because I just don't have any more details than that.
Okay.
But I understand the sedimentologic data that supports that interpretation. I can't tell you the tectonic explanation of why the slopes are different. But because the gradients of these rivers, like the northern part of the Mississippi River, has a very low gradient, you don't need a huge change in the tilting of the continent to get this to happen, because it's in the Midwest, it's just so flat, right? So it just has to change a tiny bit. So I'm going to show you another example. So this is another seismic image, and we're going to, you can see all these meander loops, like this one right there. There's another one right here. There's a big one right here, and then another one right there. And these have been traced here. There's 5 kilometers. And this is from a study published in 2018. So, not that long ago, 8 years ago. And here's the main channel going north. We know it's going north because there's pale currents. This is also in Alberta. This is the lower Cretaceous of Alberta again. This, came out, as I said, just a few years ago. And, if we look at here's a close up. So the image isn't quite as nice, but you can see these nice arcuate scars like that. Okay. And then here's the abandoned channel. We know these abandoned channels are filled with mud because they've been cored, so many places. And so again, the sedimentology of these deposits is identical to the sedimentology of the modern Mississippi. So we know this is these are rivers. I mean, they have terrestrial fossils, and so here's another one where you can see this, very narrow meander loop, and you can see the meander scar. So this is all sand in the meanders here, and then this is the mud-filled abandoned channel, just like that one from 1733. So we can compare this now to the Mississippi River. So here's on the right is the tracing from the seismic. On the left is the Mississippi River. This river has Devonian limestone below it and marine shales above it on the right from Alberta. On the left, we're seeing the modern Mississippi. These maps are at the same scale. There's 5 kilometers there. There's 5 kilometers there. And, the scale of these loops, of these meander loops, abandoned meander loops, are identical. And as I said, maybe 40, 50 meters a year, 50, the numbers are nice because it divides into 1,000 really nicely. So 1 kilometer is 1,000. So this is maybe 8 kilometers here, another 5 kilometers here. So if you add up all the time that's needed to make all these meander loops, so this one is cutting into that one, this one is cutting into that one, this one is cutting into that one, you need hundreds, if not thousands of years to form this. And so and that time is right in the middle of what's supposed to be a 1-year flood. And the sedimentology doesn't allow you to do it in less time. Like the sedimentology of the trough crossbeds and current ripples and soils, it just doesn't allow less time than that. And that other one was published in 2011. This one's 2018. I've never seen any creationist deal with these kinds of deposits. And these kinds of seismic images are not rare. We see them a lot. And so there's lots and lots of published examples. And there's exhumed examples where you can look in Google Earth where the land surface is eroded down to a sand layer, and you can see these point bars beautifully preserved. You see it in the Cretaceous, you see it in the Triassic. And so they're very common features throughout the stratigraphic record. It's wherever we have data. A lot of this is constrained by petroleum data. Collecting this kind of seismic is just insanely expensive, right? I mean, academic researchers could never afford to collect this. It's, millions and millions of dollars to collect this kind of data. And so the reason that we do this is because of the petroleum. In this case, these sandstone, these are called point bars. These sandstone filled point bars are filled with oil. And so you don't want to drill a well into the abandoned channel because that's filled with shale. You want to drill into this, and the only way to figure out where that is, you can just drill randomly and hope you hit sand, or you can shoot this seismic, and it's, thousands and thousands of dynamite blasts with very sensitive recording devices to record the echo as it comes back, and then processing it on supercomputers. And then you can say, if we drill in here, we're going to hit oil saturated sands. If we drill here, we're going to get shales, which you can't make money by drilling shale. So that's why this data is collected. It's collected in order to drill, to collect the petroleum more efficiently. So you want to spend, and it turns out with the economics, it's actually cheaper to shoot the millions of dollars of the seismic than to drill random wells. So does that make sense? Is there anything I've said that is unclear?
No, that's good.
Okay, and I'm showing you just one level, which is at the base of the Cretaceous, but we have evidence like this at many different levels. So now we're going to get into a little bit of the public. I just want to prove that what I'm saying isn't cherry picking the data. So I did some Google searches. Google searching, as you know, isn't perfect, but it's a guide. It's a starting point. So I typed in Incised Valley, and Incised Valley is the technical name for a river valley in the rock record. They're called incised valleys. I'm not going to get into whether that's a reasonable thing to call them. That's just what they're called. And so I typed incised valley as a phrase with quotes, and then Cretaceous, and then Jurassic, and then Triassic, and I saw how many. And in Google Scholar, you can restrict the search to just terms in the title of the paper. So, when I did that for Incised Valley in the Cretaceous, I got 60 examples and 10 in the Jurassic, 5 in the Triassic. Going on to Pennsylvania, 27. So in Europe, it's called the Carboniferous, and you can see not huge numbers, but this is just what's in the title. If you do fluvial, which is the word for rivers, you get hundreds of publications. And, I didn't read every one of these. In fact, I read very few of them, but I looked at the titles of almost all of them, and they're mostly on, directly on point. And then I did it for Paleosols, and this is again in the title. So the title would have to have Paleosol and Cretaceous, or Paleosol and Pennsylvanian, or whatever. And there are.
I want to object to this methodology because people will do the same thing with evolution. They'll like, oh, you want evidence for evolution? Just search evolution on Google Scholar. You'll see thousands and thousands of articles. Yeah. And if you actually read those articles, you'll see all the problems with evolution. So just having a thing in the title doesn't really give me evidence for what is being proposed.
Well,
so
if you type evolution, I've watched your videos where you've discussed that, and it's true that when you type evolution is such a broad topic. It's an interpretation, but these are very narrow terms. Like Paleosol just means one thing. It means soil. I mean, it can't mean anything else. And so if you have the word Paleosol in the title and Cretaceous in the title, there will be an example of a Cretaceous Paleosol in the paper. So I don't think your objection works for this, although.
People will say the same thing about those evolution articles. See, this article is about the evolution of the circulatory system. And then, so it's proposing to be about the evolution of the circulatory system. But then you keep reading and you find out, okay, we actually have no clue how circulatory system has evolved. But since it evolved, here's how we think it happened, right? So
that's still different than this,
okay.
Because, and I've read I can't say I've read all 500 publications of the Cretaceous, but I've read hundreds for sure. And I've probably read, for the 135 examples of river facies, or certainly the 27 in the Pennsylvania, I've read all of those. So I'd say I've read the majority of these papers, and they are exactly what they propose to be. And so there are, I think this, I understand what you're saying, and I'm not disagreeing with it, but that doesn't apply to this, because these are far more specific than just evolution. This is, very specific to, these particular types of deposits. And then if you go for, so I guess you won't like this either. If you go for, instead of just doing the title, you just do it for the words occurring anywhere in the paper, you get hundreds of thousands of publications. And so, I haven't read 100,000 publications on Cretaceous fluvial systems, but I've read probably 1,000 papers on Cretaceous fluvial systems that are on point. And so just based on what I've read and, my personal experiences, is there are, without a doubt, tens of thousands of directly on point publications that show examples of river systems, valleys, and soils in the ancient. And it goes all the way back. It's all the time periods going back to the Precambrian. And that's the major point I want to make. Like, I've shown you examples, that I happen to have worked on from the Pennsylvanian and from the Jurassic and from the Cretaceous. But these are just the examples I've happened to have worked, but there are examples in all these time periods. And so, one of the things that creationists say is, well, look at these widespread marine deposits. There's nothing like this forming today, which is true. There is nothing like that forming today, except maybe Hudson's Bay. That's really the only place. But they're separated by these valleys with soils and river channels. And then you have more widespread marine, and then you have more valleys and river channels. Certainly more in some periods of time than others. And so you need time for all those features to form. So, so here's a couple of points. There is no sedimentologic difference between flood, pre-flood versus post-flood. We went through the list last time, and I'm going to repeat it here in a minute. And there's virtually no sedimentologic difference between what we see being deposited in the ancient versus today. Like, the fossils are different. You don't get dinosaur bones forming in river channels today, but the sedimentology is identical, with a few big exceptions, like the Solnhofen limestone is an exception. The end Cretaceous asteroid impact is a big exception. But those volumetrically, those are tiny, volumes. The vast majority of the volume of rock is sedimentologically identical to what's forming today. So I just try to simplify this. IVF for incised valley fills. It's just the technical abbreviation for river valleys. And then river channels and raindrop imprints. I showed you examples of those last time. And then current ripples. I just show these as examples of the kinds of sedimentary structures we find. I like raindrop imprints because it takes very specialized conditions in order to preserve a raindrop imprint. And so the fact that they're getting preserved means that if there was an animal walking around, we would see the footprints. And from the Pennsylvanian on, it's very common to find footprints associated with raindrop imprints. But before the Pennsylvanian, certainly before the Mississippian, there's none. So, you can't make a taphonomic argument that there's no vertebrate fossils in the Precambrian, Cambrian, Ordovician, or Silurian, no terrestrial vertebrates because of preservational biases or environmental biases, because the environments are the same, at least in small areas. And then,
I guess I would like to see specific examples of that, because
I've shown you as many as I can. I mean, I can.
Of raindrops, because from what I'm understanding is that what I'm saying is I would like to see examples from actual pictures of what you're talking about and which layer this came from.
I showed you last time.
Okay, and which layer did that come from?
I showed you examples of raindrop imprints from the Pennsylvanian. Maybe 2 examples from the Pennsylvanian, but there's lots. I mean, I've got raindrop imprints in flagstones in my backyard.
And what are you saying are the preservation conditions that would cause raindrop imprints to be preserved?
Well, they have to form out of sediment that is above sea level, because raindrops can't fall below sea level. And then the sediment has to be covered quickly to preserve them.
So like the kind of thing that maybe a flood would cover.
Well, yeah, like when high tide comes up, that's a flood. And when the tide goes down, you get another layer with raindrop imprints, and tide comes up again, and that's a flood. And then tide goes down, you get another layer of raindrop imprints. So yeah, I mean, one of the sites we worked on in Kansas, we excavated 190 or so lamina, and about a third of them out of the 190 had raindrop imprints. So it wasn't one flood, it was 190 floods. And we interpreted it as tidal, that this was a tidal flat. And so you had 2 floods per day in that system, we interpreted it as 11 months worth of time. So yeah, it's not, nobody is arguing about whether North America was flooded. Everybody agrees with that and has agreed with that for over 100 years.
And Africa and Asia and all the big land masses.
Yeah, I'm just talking about North America because that's
right
where we are and that's what I know. But all over the world. It's just what happened in between the floods and how many events that is. And it's got to be a lot because of all these valleys and soils that interrupt the succession. It requires time. So now we're getting into paleontology. So we've got soils that go all the way back to the Precambrian, lots and lots of soils. And there are many publications on this. And I've shown you, the insect burrows of the soils in the Jurassic. And there are, so there's 3 processes that form soils. One is biologic. So that's, you'd think that would be roots, but roots tend to rot away. What really, it's rooting to some extent, but it's really insect burrows. That's really what the biologic aspect is. And insect burrows, because they're burrows in the sediment, they can't rot because a burrow can't rot. And so you tend to get them preserved. And then the second is mechanical, and the mechanical deformation that forms soils is wetting and drying. So when you wet the soil, a lot of soils have clay minerals that expand when they get wet. And then when they dry, they contract. And when you go through hundreds of those wetting and drying cycles, it forms very specific features that don't form from any other process. And then the third is chemical. So rainwater, because it has dissolved carbon dioxide, which forms carbonic acid, will actually dissolve minerals from the top and then deposit them at the water table at the bottom. And given enough time, there can actually be a solid state deformation, a transformation where you have some minerals, clay minerals, that will transform into kaolinite over a very long period of time and concentrate certain types of ions like aluminum. But it takes thousands of years for this to happen. And so when you go before the Silurian, so there's bioturbation going back to the Silurian in soils. But before the Silurian, we still see lots of soils. There's just no insect burrows in them. There's no burrows of any kind. Roots go back to the Devonian, and then leaves and needles. I know you cited some pollen in the Precambrian. I read that article. I think it's contamination. If you look at the types of fossils that cannot possibly be contamination, like roots and leaves, there's no leaves before the Devonian. So, and there's no way a leaf fossil can be contamination, and there's none. So, we see, and what's really interesting is, I told you there were different kinds of river systems, meandering, braided, and anastomosing. There's a huge shift in river systems that occurs in the Silurian to Devonian, where the interpretation is that the development of roots changes how cohesive the bank material is, and that changes the morphology of the river. The river is responding to the occurrence of roots. So before the Devonian, most of the river systems are interpreted to have been braided, and then after the Devonian or in the Devonian, it transitions, and most of the river systems that are preserved in the rocks, We don't know what river systems existed outside of that, but what's preserved in the rocks is meandering. So it's multiple lines of evidence that are showing you that the plants did not exist in what's preserved before the Silurian. And
well, I don't know. I mean, I'm not sure. It seems like there could be a different interpretation to that. Like, I'm you probably have a response to this, but if we were right now to, start like burying things in a flood, right? Sediments and things started moving around, it wouldn't be the like leaves and things that would be getting buried first, right? I mean, we would have marine organisms getting buried first. We would have, and that would probably happen for quite a while before any leaves got buried.
well, that's where it comes back to the raindrop imprints. The raindrop imprints that we see right here, this column, going all the way back. So whenever we see raindrop imprints, we know it's not a flood, right? Because you can't form raindrops underwater. So the
Right.
sedimentology tells us that, so we're only talking about the portions of the sediments that are subaerial. We're not talking about the widespread marine units. We're talking about what's between the widespread marine units, which is where we get the rivers, the river channels. And so, that's the importance of showing the raindrop imprints here.
Right. But are you saying that every river right now that could possibly be buried would also bury leaves along with it?
Yes. Yeah. You see
Okay.
leaves.
What about along the Colorado River? Because I've been to places along the Colorado River. There's no leaves.
Well, the Colorado River is not the kind of river that gets preserved in the ancient. We don't see any Grand Canyons that are buried in the ancient. So there's a preservation potential. So what would happen is, areas that are uplifted like mountains, they don't get preserved because the mountains get eroded away. What gets preserved is the low relief land areas that are gradually sloping away from the mountains where all the sediment is being deposited. That's what gets preserved. So rivers that are in these steep V-shaped canyons, like the Grand Canyon, that has no preservation potential long term. So we don't see anything like that. There's no place I know of where there's a canyon like that, like even 1,000-foot deep canyon, let alone 5,000 feet. It just doesn't get preserved in the rock record. It gets eroded away. So all of the river channels or river valleys that we see are in the rock record. And I shouldn't say all because there's always an exception in geology, but almost all are in low relief areas. So if you want to look
well,
for
like I said, I think you're making a good objection with the river channel thing, and I would like to hear a creationist response to that. So if there's any creation geologist that wants to respond to that, would be very happy to have you on my channel. And or if anybody wants to forward me a video where someone is responding to this, that would be great.
So if you want to know more about paleosols, I've only covered it a little bit. There's a couple of videos by this guy, Stephen Mitchell. I happen to know him because we worked together at Exxon. He's retired like me, and he has 2 videos on paleosols, he says, from a Christian geologist. One thing I'll say is that the sound quality in these videos is just absolutely horrible. So you have to get past that. But the content is very good. And then there are so many paleosols that have been described that these are all summaries of paleosols from the rock record. And again, it's not just that we find soils, it's we find specific types of soils that are equivalent to the soils forming today. So I want to review quickly the objections to soils. The main one I've seen is from Michael Ord. He has 3 objections. One is that he says most soils today have a rich organic horizon, which is missing in the ancient, but most soils today, sorry, I'm getting dry mouth. Most soils today do not have an enriched organic horizon, so that's just not true. Second, he says that horizonation is an important process in the formation of soils. That's where you have like the chemical alteration proceeds from the surface down to the bottom, and you get different zones with different chemicals, different types of minerals in them. He says erosionation is important today, which it is, and you typically don't see that in the past, which is not true. And then he says there's hydrothermal alteration that can produce soil-like features, which is absolutely true. But hydrothermal alteration just occurs around a hydrothermal vent. It doesn't form horizontal layers that go for over 100 miles, and it doesn't form insect burrows. So I haven't seen any objections that are actually consistent with the evidence. So I showed this slide before, and this is the criteria that have been listed by lots of creationists for the recognition of flood deposits. So after looking at all this evidence, we'll go through this one more time. So the first one is, and we did this at the beginning of part one, evidence for rapid deposition. And, you know, everybody agrees with this. There's no disagreement that all this evidence for rapid deposition is absolutely true, but there's also a lot of evidence for slow deposition, such as bioturbation in soils and such. Abundant fossils in the rock record. And this is a new one I forgot to put in last time, that some people say that fossils are not forming today. And that's not true. Fossils are forming today in large numbers. There's a type of limestone called beach rock that is forming in the Caribbean, in the Bahamas. It's got modern bottles incorporated into the limestone, not just on top, but like as part of the limestone. So we can date it just based on human artifacts. And we know they're forming fast. How fast is not clear, but certainly less than a year, I think. And how fast it isn't clear. And this has been known for decades. This has been known. I tried to trace it back from modern bottles. I think that's modern bottles have been observed in beach rock since the 1960s. And so this has been known for decades that limestone can form particularly fast. Other types of rock cannot, but limestone can. Marine fossils in the middle of continents and widespread thin marine strata, these have been used as evidence of the flood. And everybody agrees that there are widespread marine strata in the middle of the continent and that these are evidence of floods. But whether it's one flood or many, I think when you look at all the intervening layers, it's many floods. Creationists have claimed there's little or no soils or karst in the rock record. That's just not true. There's lots of soils in karst. Karst is a term for freshwater weathering of limestone, forming caves and collapses, sinkholes, that kind of thing. Very little bioturbation. That claim has been made recently quite a bit, and it's not true. That study, well, I'll just say it's not true. There's lots and lots of bioturbation in the rock record, and it's well documented. No river channels and no river valleys. This is said specifically by Dr. Warner and Dr. Clary in recent interviews, and I've shown, I think, abundant evidence that those are, in fact, both of those things are common. Little or no erosion unconformities. This comes mainly from the Grand Canyon, where you see, you know, some of these unconformities. There's one unconformity that has the missing Cambrian. I have to do it in order. Silurian and Devonian. No, it's Ordovician and Silurian is missing. And so it's over 100 million years in radiometric age, and it's a flat surface. There are some erosional scours there. I haven't looked at it since I was, you know, I don't know, 13 years old. I went to the Grand Canyon, but obviously I wasn't thinking about that. I don't know how that happened. I haven't studied it, but I've studied in the course of my job hundreds of unconformities, and they almost all have widespread erosion and sometimes soils as well. You know, I study them in the subsurface so I can see the erosion, but seeing the soils is tough. And then lack of complete ecosystems. This comes from its genesis history, and you know, we see in these Pennsylvanian incised valleys that there are, for all practical purposes, complete ecosystems with terrestrial animals and lots of terrestrial plants and insects. And so, you know, that looks pretty complete to me. So, you know, the reason I wanted to give this presentation is because I heard so many people saying things that just aren't true about erosion and soils and river valleys in the rock record. And it's not just that they exist, but they exist in abundance. And so all the criteria that creationists have laid out of what you should see if the earth is ancient and if the if the stratigraphic record records a long periods of time, exists, and it exists in abundance. And so, I think I'll leave it there for now. We could talk about more, but yeah, I'd be interested to hear your comments.
Okay, thank you. Well, I'll just go through this list and kind of mention the things that are still on my mind. So,
Sure.
you know, you said nobody disagrees with this evidence of rapid deposition, right,
Correct.
with the upright trees, but and complete fossils and things like that. But the issue is that a lot of times things that would be like considered millions of years layers, right? When we find something that makes it show that it's not millions of years of layers of sedimentation, okay, then the story changes for that particular sediment. But you still want us to believe for all those other layered sediments, those are all millions of years of deposition, right? So that's an issue to me, is that if we look and we see, okay, we see this all these layers of sediments, and why would we interpret some of those as, okay, this has to be millions of years of layers of sediments? Oh, but if it happens to have a tree through it, okay, we know it wasn't millions of years, but it looks just like the other sediments. So what's going on with that?
A couple things. So first of all, we don't claim that it's millions of years, except when we see fossil trees. The sedimentologic evidence is compelling as well. So when we see an upright fossil tree and we see the kinds of sediments it's buried in, even if we didn't have the upright fossil tree, commonly there's evidence of rapid burial. And so there's a lot of things I haven't gone into. And so there's no a priori assumption that the depositional rate must be slow or high. But certainly fossil preservation is something that is used to indicate depositional rate in a non-quantitative sense. It's hard to pin it down to a year. But then where we see slow deposition, we have positive indications of that, like bioturbations in soils and karst and river valleys. And so especially soils, I mean, you can't form a soil instantly. So, and then there's a lot of sediments where we don't know, where you see a trough cross-bedded sandstone and another trough cross-bedded sandstone on top of it. You don't know how much time is between there. So we just say we don't know. So I don't agree that it's the default position that must be millions of years. There's sediments where we see evidence of long periods of time and soil development, sediments where we see evidence of very rapid deposition and fossil preservation, and then sediments where we don't know.
Okay. And then the other thing is, I realize that you gave some examples of fossils still forming today. But for me, one of the obvious examples of or evidence for a flood is that I don't see happening today these massive sediments forming massive fossil beds, and ones that are mixed with marine organisms, like the Hell Creek Formation. You've got whole dinosaur fossils mixed with whole shark fossils. And so I don't see anywhere in the world where and over a massive land area. And so I don't see anywhere in the world where that's happening today. And that is what the massive amounts of sediments is what characterizes the sediment across the earth. Like we talked about the mega sequences and such. I don't see anywhere today where something like a mega sequence is being formed, that much sedimentation. The biggest sedimentary deposit that's happening today is the river delta in India, right? And that is like very small compared to one of these mega sequences that we see that does show evidence of rapid deposition because of the types of fossils, the amounts of fossils, the consistency to the sediments. So that's one of my objections. I'm just going to go through the whole list real quick, and then you can say a final response if you want. But then I have heard this about little to no soils or karst, and I realize you've given some examples of soils, ancient soils, but like, in just my personal observations, everywhere that I go in the world that's not covered in foliage has sedimentary layers that are right on top of each other, that are not bioturbated, that, and don't look like they have a soil there, a soil layer. So, and I have some pictures of various things that I'll pull up in a minute, and I'll get your feedback on those. And then, of course, all over the world, I also see mountains and rock formations that are bent or wavy. And so it looks to me like those would have had to be soft when they were formed. Because if they were hard and then, another layer was formed or uplift happened, then they would have cracked, they would have broken. But they're like bent and wavy, and they look like sediments that were rapidly deposited and then uplifted and causing the bending. So, and I'll pull up pictures and I'll let you respond to those pictures after I get through this.
Can I respond to that one thing first?
Okay, sure.
So, I showed the examples from the Pennsylvania of Kansas where there were chunks of limestone in the valley fill. So we know that limestone was hard rock before the valley was eroded because we've got chunks of it in the valley. So limestones can form fast. So limestones are, there's lots and lots of evidence that limestone from the ancient was rock hard before it was deeply buried. About sandstones, sandstone requires, especially quartz cemented sandstone, does require deep burial and lots of time. There is, for the bent layers, it's pretty easy to find examples of cracks. Most of them you have to get up close to see the cracks, but there's lots and lots of cracks in the bent layers, and they form these crack networks called joint networks where you can actually work out the stresses and strains that were occurring at that time. And that's really well documented. So, but sometimes you have to get up close to see them and to see the cracks, but they're absolutely there. There are some sediments that have been deformed, especially shales tend not to be cemented very hard, and so they can deform plastically without cracking because the clay minerals slide against each other. And so it depends on the situation. But all the things you're talking about that should be there are there, like cracks and rocks as a result of deformation are very common.
Okay. So, and then I think that you made a good objection with your river channels. I would like to hear the creationist response on that. And you say isn't it one, and so I'm waiting. If any creationist has a response, great. And so I don't really have any pushback against that. I do have the pushback about the little to no erosion at unconformities, because I have seen pictures like at the Grand Canyon where you have the Great Unconformity and then you have another layer right on top of it. And there's supposed to be like hundreds of millions of years that this should be being eroded before this next sediment, right? And you don't have that. You don't have it, that kind of erosion happening between those layers.
Can I comment on that? That one?
Sure.
So at the Great Unconformity, there are places where that unconformity is very flat, but there's also other places in the Grand Canyon that shows quite a bit of relief on that surface. And, when you look outside of the Grand Canyon, you do see a lot of relief on that surface. At the base, we talked about earlier the river channels at the base of the Cretaceous in Alberta. And when you look at it in the subsurface where you have those seismic images, you can see a lot of irregularity in that surface. But when you go up to an outcrop, it looks flat. It just looks flat. You just have to have a bigger area. Now, those outcrops aren't anywhere near the size of the Grand Canyon. So, but there is absolutely erosional relief on the Great Unconformity at the Grand Canyon.
But hundreds of millions of years on the places, even where it's eroded, is it hundreds of millions of years worth of erosion?
Well, the this gets into another topic that is, yeah. So I'll just get into this very briefly. So when rivers erode, as rivers sweep back and forth, you can imagine the base of the river channel eroding a surface that was never subaerially exposed because it's the base of a channel. And as over millions of years, as it erodes the base of a surface, there's something called the equilibrium profile, where the river will erode down to a certain level and just can't erode deeper than that. And so as it sweeps back and forth, it will make a surface, an erosional surface that's fairly flat, not perfectly flat, with some relief on it, but it just it takes a long time, but it can erode quite a flat surface over a long enough period of time. So actually, the length of time is actually inducive or conducive to a flat-ish surface over a wide area.
Okay. Well, I wanted to pull up these pictures and
Sure.
just get your thoughts on this because, this is the type of stuff that I see and, the type of stuff that I see all over the world that makes me think, okay, this this looks really strange if this was deposited over millions of years. So how do you look when you look at this, what do you see?
Yeah, I'm just trying to adjust my screen so I can make it bigger. And I can't. Okay. So, whether it's millions of years or not, I'm not familiar with, I've never been to the Alps in Switzerland, so I can't say, but you'd have to look at the specific sedimentology. So there could easily be, soils and karst in that area. You don't know. So it's not whether the rocks are bent, it's what's in the specific layers. And are there soils? Is there karst? Are there coral reefs that could have taken thousands of years to form? So that's the question, is what's happening at the small scale.
Okay. So here's just a couple more
Yeah,
examples.
that's at the Grand Canyon, I think.
Mhm.
And yeah, it's hard to see. There's no scale in this photograph, but there's a lot of these kinds of bends that are just filled with small cracks. And so,
Right,
and
filled with small cracks, but like still bent in a way that it would be hard to see how solid rock would bend that way without breaking.
uh, this is getting a little bit outside my area, but if it's buried deep enough and gets hot enough, the rock can deform plastically. And there's also shale. So this looks to me like sandstone and shale, and the shale layers can slide past each other. So it's really the sandstones we're talking about. And if it's hot enough and it happens slow enough, you'd have to look at the deformation of the individual quartz grains.
Mhm.
And I'm now, you know, already beyond the limit of my expertise. I know that this can happen if it's deeply buried and hot enough and slow enough.
Okay, and actually that brings up another thing that I wanted to bring up, which is overthrusts. So,
Yeah.
places where there's really not evidence of the sliding, but they say that it had to have slid over, right? Because it's a layer that doesn't belong in that location.
So I've actually worked thrust belts in Wyoming, and I've never seen a case. I'm not a structural geologist, so I haven't worked it that much, but I have worked enough examples, and I've never seen a case where there isn't evidence of the movement. And commonly, so what a thrust fault is, it's a very low angle reverse fault. So it's where if you have a continuous layer like this and it fractures and one part can ride up over the other part like that. So I'm just trying to get this to the camera so you can see that you're talking about something like this. And
Right.
so when you do that, the way you can tell that it was, one of the ways you can tell is that if you take a map view and you look at this edge here, and then you look at the edge that was broken, you pull them back and they fit together, like the pieces fit together like a puzzle. So all the little indentations and irregularities in the piece on top fit together in the same, like a jigsaw puzzle on the bottom. So you can, in fact, that's one of the tests that we do in petroleum geology, is when you're taking those thrusts and you want to work out the fault framework and try to make the best prediction you can about the reservoirs in the subsurface, you better be able to pull those faults apart and fit them back together. And if you can't, you've probably done something wrong. So, and it can get complicated because there can be faults on faults and faults and faults. And I worked a reservoir in Wyoming, where the reservoir was actually repeated 4 times in one well. You had the reservoir, then you had the reservoir, then you had the reservoir, then you had the reservoir. And so in seismic, you could actually see that. You could see the thrusting. So yeah, I've never seen an example where there's not really good evidence that the thrusting has happened.
Okay. And we don't have to stop at every picture, because this is just another illustration of,
Where is that?
This one I couldn't figure out where it was, so I don't know.
Yeah, you could do a reverse image search. Yeah. Yeah.
This one's in Oman.
Did you take this?
No.
Okay.
But what are your thoughts about how something like this would form?
Well, without knowing the age or what lithology, I mean, I've seen things like this in evaporites, and evaporites can deform plastically. And so it's really hard to know without, I mean, there's nothing in here for scale. There's nothing in here to tell me what the lithology is. So there are some, to me, it looks like an evaporite succession, just based on the color. I can't say that for sure, but that's what it looks like.
So what is an evaporite succession?
Oh, sorry. Evaporites are minerals that form from the evaporation of water. So especially seawater. So as it evaporates, one of the common minerals you get is gypsum. And this just looks like gypsum to me, but I could be totally wrong, because and then gypsum is soft, and so it deforms really easily. So that's about all I could say about that.
Yeah, and I didn't go digging through all the pictures that I've taken of places that I've been, but these are just the kind of things that I'm used to seeing around the world, that every time I look at it and I say, okay, wow, massive amounts of water did something here. And so I see that everywhere I go.
Where is the evidence that this was done by water?
Well, it looks like it was at least sediments that were soft when they were deposited, right? Like,
well, almost all sediments are soft when they're deposited. But like I say, if it's
how do you move sediments around like that? You have to have massive amounts of water to move sediments around.
No, you can do it with tectonic forces.
Okay.
So, this may have happened deep underground. We don't know. It's important for these examples to know what the specific lithology is. And it's really hard to say that. Now, this one I can describe. I probably know where that is. That's the Dead Sea.
Mm-hmm.
Yeah. So that absolutely is by water. If you can zoom in onto the lower right one, can you zoom in on that?
I don't think so.
Okay.
No.
So that kind of deformation absolutely happens in, I don't know the least information. I'm going to Google that really quickly here, just so I can. Oh, shoot. Yeah. I just want to see what the least information is. I think that's also. Yeah, I think those are evaporites as well. And so you can notice how you have a flat layer and then deformation and then another flat layer and then deformation. And so that's compressive deformation. And you can have sliding if there's a gradient on the surface, if it wasn't perfectly flat, and maybe there's an earthquake to trigger it or a storm, it can then slide along that surface and create these kinds of deformation features. But it's a series of events. It's not one event. So I see an event just at the guy's head, and then I see another event above that, and maybe a third event above that. But then there's even deposition in between there. So I've seen. I haven't been to the Dead Sea, but I've seen deformation that looks very similar to this, and it happens before deep burial. So it happens like the deformation at the guy's head happened before the next layer that's flat was deposited.
Okay, this one I'm sure you're familiar with, Capitol Reef.
Yeah, I've been to that area. I actually went there on my honeymoon. So these layers are flat, right? You're just seeing modern erosional relief that makes it look like the layers are squiggly. But
Right. No, and this is kind of moving on to showing that, in lots of places around the world, we have layer upon layer with no erosion in between, just, layers of sediments.
Well, you can't tell from this angle whether there's erosion there. You really have to get down level on bedding and sight along it, and then you can tell. There's a lot of the exposures in Capitol Reef. I don't know this particular spot, but a lot of the exposures in Capitol Reef are aeolian units like the Wingate Navajo and Entrada sandstones. And those are, as I said, they have sedimentary structures that are unique to windblown sand. And what happens in windblown sand systems, and I don't know if that's this, it looks like the colors have been kind of enhanced. Usually when there's red colors, it's not windblown sand, but I can't tell for sure. Yeah, I know exactly where this is.
Okay. So how do you,
So
this looks like it could be actually sand.
This is sand. I know exactly what this is. This is the Navajo Formation in Utah. And
right.
I wish, is there some way I can point?
Not really. No.
Okay.
Not on this.
So notice about midway up, maybe can you point with your cursor?
Can you see it?
No, I cannot.
No. Okay. Yeah. It doesn't work on PDFs. This is a PDF,
okay.
not a PowerPoint.
Oh, I thought it was PowerPoint. So never mind. But you can see about midway up, there's bendy units, and then there's a flat surface that truncates them. So do you see that? It doesn't quite get to the skylines below that, but there's a very flat, horizontal, dark band that looks like it's made. Okay. So there are giant cross beds in this unit that are 30, 40 feet thick. I've got a picture of them in my book, although not this location, but not too far from here. And when you look at the details of these sands, this is all pure sand, pure sandstone. When you look at the details, you see things called grain flow beds, grain fall beds, and wind ripples. And all of these sedimentary units are unique to aeolian deposition. And then in aeolian units, there's usually a water table if you go down far enough while it was being deposited, not at the surface. So you have to picture desert sand dunes. And as desert sand dunes form, and they're called ergs, like a field of sand dunes is called an erg. As an erg forms, there has to be more sand coming in than going out in order to get deposition. But if that changes to the point where there's more sand going out due to wind than coming in, you get deflation. And what will happen is it'll deflate down to a level where the water table was at that time. And those are called supersurfaces. And if you walk up to that surface, what you typically see, and you can't see it in this photograph, but when you walk up to those very, very flat surfaces, what you see is usually is commonly some reddish color and some very, very poorly formed soil, insect burrows, sometimes roots, and sometimes you can even have a little bit of channel scouring from small river systems. And so you get these flat surfaces called supersurfaces that go for tens of miles. I mean, it's just amazing. And they're interpreted as the deflation down to the ancient water table.
Now, where would you see all this sand coming from?
That's a really good question, and it has not been fully answered. Like even in modern Sahara, there are large ergs in the Sahara Desert. So the Sahara Desert isn't one giant field of sand dunes. It's pockets of sand dunes separated by solid rock, and then another pocket of sand dunes, and those are called ergs. I think there's I forget, the largest erg is like millions of square miles. I mean, they're huge, but they're not the entire Sahara. And then the source, what's the source of the sand? It's just like, even for the modern Sahara, it's not clear. And it could just be the gradual wind erosion of the solid rock that's around them. There are some ergs, like in Namibia, that occur along the coast, and then you have beach sands, and the beach sand can be blown up into the erg. So for coastal systems, it's generally considered that the beach is the source of the sand, and then the waves are bringing the sand in along the beach. But for mid-continent ergs, the source of the sand isn't fully understood.
Okay. So
Oh,
here's
this is
another
Bryce.
one.
Yeah, I've been
Yep.
there. Yeah, those are all soils. Yeah. Just
Okay,
one
you're saying
soil.
all these layers of sediments, this is all soil.
Yeah, that's all pretty recent stuff. It's post Cretaceous. Yeah, we I've been there, and we hiked. We did like a 10-mile hike in Bryce Canyon on our honeymoon. That was fun. And so I don't know if we went to this specific location, but we certainly were in lots of places that looked like this. Yeah.
And so what kind of fossils, since you're saying this is post-Cretaceous, what kind of fossils are found in this?
I have no idea. I don't know.
Okay.
I could look it up, but I don't know off the top of my head.
Okay, that would be interesting to find out.
Yeah, I just don't know.
But how do you know it's post-Cretaceous?
I remember reading it.
Okay. How about this one?
Yeah, this again is this is one of the Aeolian units. So yeah, I don't know. I've never been to this state park. Where is Valley of the Fire?
I don't know. I actually haven't been there either. I was just looking at pictures in Utah.
Yeah, let me look it up.
But how are you saying these layers are formed?
So according to Google, Valley of Fire State Park is in Nevada.
Oh, is it?
Yeah, that's what I
Okay.
found out. I found a photo that looks very similar. Not that exact photo, but one that looks very similar.
Okay.
So I don't know what age this is. It says on Google the Aztec sandstone, which is another Aeolian unit, which makes sense to me. But it's hard to tell from this angle what that is. So I'll defer on this. Oh, this one I know, Canyonlands National Park. Yeah. So that's I think that's mainly the Triassic Chinle Formation, which has soils, and there's probably some other units in there as well.
Okay, but
yeah, you're so far away that there's probably lots of erosional scours in here. You're just too far away to see it.
Right. But if, like, let's say there's, doesn't erosion and burrowing and those type of things destroy the layered look?
Remember, for marine units, the burrowing only goes down about 3 feet. And so if you're half a mile away, you're not going to see the effects of that. You'll still see the flat layers. And so the what it really counts is what you would see close up. So you'd have to be like right up with your nose against the rocks to see that.
Right. But would you say that these are layers that are supposed to have formed depositionally over millions of years?
Yes.
Okay, so how did they form over millions of years and then have no erosion to, destroy the layered look of the sedimentation?
Well, you can't, you're too far away to see how much erosion there is, and you're looking at it at the wrong angle. So in order to see the erosion, you have to look straight on exactly along bedding. So you can't be looking like that. You can't be looking like that. You have to be straight on the bedding, and then you can see the scouring. From this angle, you just can't. And so you do in the distance, the further away you go, you're looking straight on bedding, like in the middle of the photograph near the top. But there could be, large scours that you just can't see at this distance. So, and there could be, thick soils and river channels, but a river channel that's 100 feet wide wouldn't show up when you're 5 miles from the outcrop.
Okay, well, it's just, I've been on a lot of hikes and things and seen layer right smack upon layer.
Yeah,
right.
That's true.
Okay, so what's your explanation for why those layers are right upon layers with no evidence of millions of years of erosion?
Well, it depends on where you are. When I showed you the cross
In the places that you see the layers upon layers with no erosion in between, what's the explanation?
So there's several possible explanations. One is if you're in the middle of an ancient seaway that was never subaerially exposed, then you'll just get layer upon layer upon layer, and since sea level never went down. When sea level finally goes down at the top, you might get some erosion, or before that, you might have erosion. But in the middle, like in the Mancos Shale, you've got 2,000 feet of layered mud, which is now shale, and you don't see any scouring that's significant because it was never subaerially exposed for the entire Cretaceous. It was always underwater. So it depends on where you are. Also, if you're in a desert setting where there's no rain or very little rain, then you don't get rivers, so you don't get erosion. So it's case specific of where you are and when you are and what the specific conditions are at that time.
Here's another one. And
yeah, we've talked about the Grand Canyon.
Yep. Okay. What about something like this?
Yeah, those are, there's this, I've never been to that area, but I've seen things like this before. And a lot of times it has to do with the type of clay minerals in the shale. If they expand when they get wet, you get this thing called popcorn weathering. And you can kind of see it in that closest feature. It has kind of a ruffled look to it. And if you dig in with a rock hammer, you can get into the unweathered shale, and it gives you this popcorn type of texture on the surface. And it's due to many, many episodes of wetting and drying where the clay minerals expand and they contract and they expand and they contract. And over time, it produces this distinctive topography. You can see stuff that's very similar to this outside of Calgary, Alberta, in the Cretaceous sediments there. I have no idea what age this is.
Okay. So again, this is, just another place in the world. I'm just, I'm picking out just various places in the world, and this is one where I've been, and just showing that, like, I see these layers. It looks to me like this was deposited by water rapidly.
How can you tell?
Well, I'm looking at all these layers on top of each other, right? But that don't look like they have erosion between them. And I know we're not up close.
Yeah.
But it's just, they're just flat on top of each other.
Yeah, first of all, I've never been here. I have been to Turkey, but I did the archaeology stuff on the Ephesus and Izmir and stuff. So I don't know the geology of this area, so I really can't respond to it. But a lot of times you see layers that look flat in the distance. You go up close and they're not as flat as you thought they were. And you see a lot of internal scouring. And so it's just, I don't know. I'm hesitant to make a conclusion based on an area I've never been, looking at a photograph that was taken like a mile away.
Right. So, well, I wanted to get pictures that captured, the layers. And so, I will take pictures and send them to you if I go to a place that has layers like that. And,
So it's important to get some, far away and some close-up photos. If you do a close-up photo, put something like a coin or a pen in the photo so I can see the scale. And then there's an app that you can get called Rockd, ROCKD. And if you have a Wi-Fi, or if not a Wi-Fi, if you have a cell connection, or if you download the map ahead of time, you can get the lat long and it'll tell you what formation you're standing on. And then just click it and do a screen capture of that. So I know what unit you're looking at. That would be very helpful. And then I'm glad to offer input. But those two things, scale in the photograph, distance far away, close up and far away, and at least what latitude and longitude you're at, which you can get from your cell phone, even if you have no cell connection, you can get that. And then that'll help me cite where you are and what you're looking at.
Okay. Well, thank you for sharing all that you shared today. And I think you've brought up some good objections to the flood scenario. I will tell you that I still see like massive amounts of evidence for a global flood. So there's anomalies. Yes, I will admit there's anomalies, and I don't have an explanation for those anomalies. But overall, it still seems to me that the flood scenario is a better overall explanation for what we see. I know you disagree with that, so I'll let you make a final point about why you might disagree with that.
Yeah, the reason I disagree with that is river channels, river valleys, and soils. I mean, they're just so ubiquitous in some areas, not everywhere, but in some areas. And I don't see any way around having so much time, thousands of years to form the soils. And so nobody says there wasn't a flood. It's just that there were lots of floods with long periods of time in between them. That's my final say.
Well, one thing I didn't really give you a chance to respond to is when I mentioned formations like the Hell Creek Formation, where you have, massive fossil beds that include things like dinosaurs and sharks, T-Rex and a shark in the same area. So how did that happen geologically without, a global flood?
I'm not that familiar with the Hell Creek Formation. I'd have to look up why, what the distribution is. I'm just not going to speculate, because I started to look it up and then you started talking about something else and I stopped looking it up. So I'm pointing to my other screen, my other monitor where I had Google. And so I would need to look that up and see why. I'll state what I stated before. When you look at the details of deposits, the vast majority of terrestrial deposits terrestrial fossils are not mixed with marine fossils. There are a lot of cases where they are. And if you're like near the shoreline, and what I saw in the Hell Creek Formation, from what little I did look up, is it's not complete shark fossils, it's teeth, individual shark teeth. And so you could have, and I don't know if this is the case there, you could have river channels that can erode into a marine deposit, and shark teeth are extremely durable. And so they could be eroded and redeposited as part of a river, just like you can have rivers today that are eroding fossils from the Ordovician and incorporating them into the sediment of the river. For the Morrison, you can make the statement the Morrison Formation has both marine and terrestrial fossils. Yeah, but not in the same place. They're separated out either geographically or stratigraphically. That in the Morrison Formation, the vast majority of dinosaur fossils do not occur anywhere near marine fossils. But there are marine fossils in the Morrison Formation, but sometimes at that stratigraphic level, you might have to go hundreds of miles to get to where they are. So the fact that you have marine fossils and non-marine fossils in the same formation doesn't really mean anything. But I don't know. I can say that for sure about the Morrison because I know the Morrison very well. I don't know anything about the Hell Creek Formation. So I'd have to look up. What I'd want to see is a map showing this is where T-Rex is. Like, has anybody found, a shark tooth, say, in the same layer, in the same outcrop as a T-Rex fossil?
All right. Well, that's a good thing to put me to work. I'll look that up for our next talk. And thanks so much for being here and sharing your expertise.
Thank you for having me.